Could I ask you to take your seats, please? So good morning, everyone. I'm Sheila Rowan. I'm the Physical Secretary and Vice President of the Royal Society, and it is my extreme pleasure to extend to you all a very warm welcome, both those in the room and those delegates who will be joining us online, and we have a substantive number of those. I particularly want to welcome those for whom this is their first time in the Royal Society, and also those who've travelled quite some distance to be with us today. I know we have some international folks who've come from overseas, and it's wonderful to have such a great turnout for this event. So the Royal Society is the independent scientific academy of the UK. Its mission is to promote excellence in science for the benefit of humanity. Today, we have an event that will discuss recent and prospective advances in quantum innovation, including quantum-based computing, networks and sensing systems. We will celebrate cutting-edge science, but we also are encouraging our speakers and our delegates to consider the scientific and technical challenges that the field faces. And in doing so, we're extremely fortunate to have a really superb lineup of speakers, of panelists, and of chairs for the different sessions. Before we get started on the exciting part, I have the duty of giving you a little bit of housekeeping information. If you need assistance during the conference, please look out for Royal Society staff. You'll see they're either wearing gold badges or red lanyards. There'll be someone on the registration desk both today and tomorrow, and there'll be others around the room, so please don't hesitate to ask if you need help with anything. If the fire alarm sounds, it will not be a drill. So please exit the building as quickly as possible through the marked signs and congregate at the Duke of York steps, at the top of the steps, and Royal Society staff will help. Okay, housekeeping over. It's a tremendous pleasure to welcome two of my colleagues to the stage to kick off the meeting. Can I invite Sir Peter Knight and then Sir Tom Grinier up to the stage to start us off?
So what we have is the International Year of Quantum. It's 100 years since Heisenberg started the quantum revolution of actually understanding microscopic matter. It's transformed the world, and we're very lucky to have been able to persuade the United Nations and UNESCO to actually generate a year of programs. Now, I chair the UNESCO steering group for the International Year of Quantum. We look after the global stuff. And what we want from this, well, what do we want from an international year? And in my view, there's one thing that we really have to do, which is to enthuse that next generation about the importance of the subject, to bring people in. I don't know why we're looking at that slide. We don't need that slide yet. To bring people into the fold, listen to them about how they're going to contribute to the way that quantum is going to be transformative in terms of societal value, economic value, and so on. I think during that year, there'll be global events, and that's what my own committee has to look after. But right around the world, there's going to be thousands of individual events which we're going to be fostering and encouraging and supporting wherever we possibly can. I think at the end of that time, we'll be able to demonstrate the commitment to this, the way it's going to transform people's lives. Within the UK and Ireland, and I notice I've added Ireland to that, we have, very fortunately, we have the Institute of Physics, which represents the UK and Ireland in this space. And the UK program is going to be coordinated by a community that's being led by the Institute of Physics. So Tom Grinier, the Chief Executive of the Institute of Physics, and his team, including Lewis Barson, who's actually on my steering committee as well, what we're going to be doing is working with you to actually see how we can run events around the nation as well, all 4 nations, in fact, of showing how quantum is going to be transformative. So if I bring Tom up now, Tom's going to say something about that. And I'll come back to the global program at the beginning of my own talk in a moment. But Tom.
Are there a couple of slides on this? Good morning, everybody. I'm Tom Grenier. I'm the Chief Executive at the Institute of Physics. I don't think I've ever followed two past presidents of the Institute of Physics, and both who've done so much for the world of quantum, both Sheila leading the Quantum Skills Task Force, and I think Peter spearheading for decades now the UK quantum effort. And I just wanted to say a couple of words about the role that the Institute of Physics is working on over this year. On the 7th of June in 2024, the UN ratified this year as the International Year of Quantum. And to begin with, it felt like we were playing catch-up. Catch-up in a number of ways, because normally international years come along a year and a half out, but the global picture had meant that it was a fairly late decision. That said, it was an incredibly important one for the science community and in particular the physics community. So the Institute of Physics was absolutely delighted when we were asked by DCIT and the UK government to spearhead our efforts. My colleague Lewis is going to talk in more detail at the end of the day about all the various things we've got planned during the year. But if I wanted to emphasise one thing Peter said, it's the opportunity that exists across this year for us to promote awareness. In particular, we're going to have events throughout the year. Do go on the IOP website. Do go on the various other partner websites that you'll find linked to there, including the UNESCO website, to look at what that UK, and as Peter said already, Irish activity looks like. And really for the IOP, it is a continuing journey. It's a journey that, for me, began a couple of years ago at the IOP when we launched our report into the future of quantum technology that helps shape the UK's quantum strategy. And then, as recently as 2 weeks ago, saw us with Sir Peter and other colleagues in the room at the global launch of the International Year of Quantum at UNESCO, where there were 1,000 delegates. I'm really pleased today that both in this room and online, we've got almost half that number of what we're seeing as the UK's launch of this International Year of Quantum. As I say, at the end of the day, Lewis is going to go through in more detail in terms of the various plans that we have for the year. But the one thing I would point out is that we're targeting November in particular as being the UK's month where we're really putting that flag in the ground to mark the International Year of Quantum in the UK. Germany have already gone in January, France have already gone in February, and then we're cascading through the year, taking individual months. The other highlight for us, I think, is going to be in June, where we're looking to host a quantum exhibition for a week in the House of Parliament. It looks like we're getting that date finalised now. But again, in that promoting awareness, it's a real opportunity for us to get the opportunity across. When prior to the election, when I was briefing one of the parties who were pulling their manifesto together, I was told, don't talk to us about quantum in Parliament, we don't know what that means. That is the challenge that we have. As my physics teacher used to say to me, word longer than marmalade coming up, quantum isn't even longer than marmalade, so we must get it across to our decision makers. So thank you for offering the opportunity to launch the International Year today in the UK, and now I think I'm handing back to Martin to introduce Sir Peter more formally for his address. Thank you very much.
Well, thank you. Good morning, everyone. So I'd like to add to the welcome on behalf both of the organisers of this meeting and also on behalf of the Royal Society's Science, Industry and Translation Committee, of which I'm Deputy Chair. So this meeting has been in development now for about 16 months. It's taken a long time and a lot of effort to pull it together. But we're finally here and we have a great programme lined up for everyone. This conference is one of the SIT committees and the Science and Industry programmes transforming our future meetings. These are meetings that are very important in drawing together multiple stakeholders in areas of science and technology that have broad societal and economic implications, where the translation is moving very quickly from the science space to industry. And of course, quantum is a particular strong example of that. So having done that introduction, it's now my pleasure as chair of the keynote presentation session to invite Professor Sir Peter Knight to the stage to give his keynote. Peter has already been introduced and is known to many of you already, all of you I'm sure already, is a very senior figure in the international quantum optics community, and of course has been the principal figure worldwide really in driving the whole quantum technology agenda. So, Sir Peter, welcome.
So my job is to run through 100 years of quantum. I probably am the oldest person in the room, but I wasn't there right at the beginning. I should stress that. Okay, so, and I'm always obliged by my colleagues within the UK National Programme to put the thing in red, that what I'm telling you does not necessarily represent government policy. And I always add yet to that statement. Right, we've seen this already. That's the International Year of Quantum's ambitions. I do think that we have a great opportunity. It was spearheaded through UNESCO by Mexico, and then through the United Nations by Ghana. We will have a closing event in Ghana. So anybody with links to Africa, please do contact me, because it's a great opportunity for that. And what we really want to be able to do is not to impose on you what we're going to do during the year, but to hear from you and work out how we can help you to actually get events running. Now, I'm going to skip that because we've had enough of that already. How did quantum change our view of the world? And there's some take-home messages here that really are transformative. Now, the thing about quantum is that it's viewed by non-scientists as pretty scary. It's counterintuitive and so on. And it is transformational. What we see with the evolution of quantum mechanics, the end of Newtonian materialism, the end of local realism, the way we actually view things in terms of having intrinsic properties. We know now, through the work in quantum, that everything in the world is connected through entanglement, it's non-local. We see the end of strict determinism and predictability in nature, and it's restored the human observer to a central role because of the act of measurement. So these are kind of the take-home key things where quantum has really transformed what we know about the world. Something else as a take-home message for those who are not specialists is that amplitudes and superpositions are at the heart of everything. Now, of course, probability has been part of physics for many centuries. But what probability in classical physics represents is our ignorance of things that then becomes more precise as we acquire information. But in quantum physics, interference amongst the amplitudes for quantum events and the way that they change in our ability to measure through an intensity, for example, all of that reflects a lot more than just ignorance of it. It tells us about knowability of systems, and I'll come back to that perhaps. So the founders of quantum mechanics. Okay, Max Planck, right at the very beginning, was actually a conservative in this sort of area, but did explain black body radiation through the idea that emitters and absorbers took place in discrete events. Einstein, with the photoelectric effect, and then Niels Bohr, Heisenberg, Max Born, Paul Dirac, and so on. All of these are going to feature in what I'm going to say next in the history of these things. And there's a beautiful quote from the Cambridge Philosophical Society article that Schrödinger wrote about the nature of entanglement that I think is a great take-home message. They can no longer be described in the same way as before by endowing each of them with a representation of its own. This is really quite at the heart of entanglement. So I think that statement from Schrödinger, when he introduced the idea of entanglement, is important for us. So how did it all start? 1925 is the key year, okay? But let's look at the precursor in 24-25. Physics in 24 was in a terrible mess. We had the Bohr model, but it was in crisis. Dealing with anything other than a single electron atom was complicated. People started to worry about ways in which it could be extended. Kramers, Slater, and Bohr even came up with a theory which implied the abandonment of causality and the conservation of energy. That's how desperate people were in 24. It was focused on the correspondence principle. Those of you who come from an optics background, this thing hinged on the Kramers-Heisenberg dispersion formula, if that means anything to you. Scattering of light by atoms was the key to all of this. So people were worrying about these quantum jumps that were in the Bohr model, but de Broglie had already come up with the idea of waves, and we're going to talk about that. Okay, so how did this all start? Okay, in Easter 24, Heisenberg, on his first visit to Copenhagen, started to worry about this Kramers dispersion formula. And he already started to think about the components in the dispersion formula that suggested that amplitudes were important. Amplitudes and interference in the Kramers formula. But he suffered abominably from hay fever. Max Born, who was his boss at the time, sent him off to Helgoland, where the pollen counts were much lower. And during his time in Helgoland, he started to look at ways in which that Kramers dispersion formula could be understood in terms of those amplitudes. On his way back from Helgoland, he visited Wolfgang Pauli, and Pauli encouraged him in this because it was the beginnings of what a bit later was called matrix mechanics. Okay, Pauli was, unusually for Pauli was positive about somebody else's work. Okay, he got back to Göttingen, talked to Born. Born said, this odd multiplication rule that you've discovered is called matrix multiplication. Heisenberg didn't know. Okay, and then working with the group, Born then produced what came up with the commutation relation. That proof was properly also then extended by Jordan and also independently by Paul Dirac. So by 25th of September, they had the full theory of quantum mechanics. Dirac also the full theory independently. So what we have is matrix mechanics. And Pauli, by that time, had gone back to his normal grumpy mode. And he really hated this Göttingen formulation. Ehrenfest actually labeled Pauli as God's whip. Die Geister, I think eventually he relented. By the end of 25, the three-man paper, Heisenberg, Jordan, and Born, came up with the idea that included, at that point already, field quantization, but also implied jumps between states. Pauli, by that time, had relented and had solved the hydrogen atom spectrum using matrix mechanics. Right. So a little bit of history here. Schrödinger, who'd heard about de Broglie's waves, okay, was beginning to evolve what became Schrödinger's wave mechanics. Okay? There was a joint colloquium between ETH and the University of Zurich on de Broglie waves, and Debye actually interrupted it. And Debye said, this way of talking was rather childish. If you're going to do waves, you better have a wave equation. Now, I was told this point blank by my first ever boss in the US, Felix Bloch, who was in the room. And Felix Bloch said, he turned round and said to Schrödinger, who was sitting behind him. Schrödinger, you're not working on anything at the moment. Why don't you look into a wave equation for these de Broglie waves? Okay? And then he came up with it. It's interesting. Does anybody in the room, apart from my former students, know what that wave equation was? It's the Klein-Gordon equation. He did the relativistic one first, and then did the non-relativistic version. Right, so back to Heisenberg. Heisenberg, on a visit to the UK, to the Cavendish, visited Ralph Fowler, who ran the theoretical activity in Cambridge, and he gave a talk at the Kapitsa Club in Cambridge. And Dirac, who was Fowler's student, almost certainly attended that. And Fowler had actually shared some of the preprint ideas of Heisenberg with Dirac. And Dirac just leapt at this, but linked it back to the idea of Poisson brackets in classical mechanics. And there's Dirac. Okay. By January 26, his complete theory of quantum mechanics. He linked it to the Poisson bracket. He called it a bracket, B-R-I-K-E-T, which is kind of ironic for those of us in quantum information now. And he introduced the idea of C numbers and Q numbers, and he did the Zeeman effect, and he completed his PhD. And can you see anything remarkable about this? This is the most transformational PhD probably ever written, and it's handwritten. Okay, beautiful handwriting. Okay, and if we look, there's the abstract. Beautiful handwriting. So when you discover the theory of quantum mechanics, what do you actually do as a follow-up when you're a postdoc? Well, of course, Dirac invented relativistic quantum mechanics and antimatter, amongst other things. Right, so back to wave-particle duality. De Broglie's 1924 paper was actually a qualitative paper, but it built on ideas that were already in the air, because Einstein had already published what was called his fluctuation formula of blackbody radiation, which had a wave component and a particle component simultaneously. And it was that triggered de Broglie's idea of waves. And then on the top left is Davison and Germer, early 27, and on the top right is G.P. Thomson in 27, actually demonstrated the diffraction of electrons. And of course, it led to the electron microscope. So even these fundamental things were already transformative in instrumentation. Right, so now we have a wave function. It's in the Schrödinger equation. So what is it? Okay, Schrödinger really did think of this in terms of a physical quantity, whereas the Born and the Dirac view was very much in terms of probabilities and probability amplitudes. Schrödinger absolutely hated matrix mechanics and the idea of jumps, and I'll come back to that. But he did show that the equivalence between matrix mechanics and wave mechanics, Dirac had also done that quite independently. So now we have a quantitative theory of matter at the microscopic level for the first time. And that led to our first quantum revolution. And it transformed society. It led to the way in which we understood the fact that there are discrete energy levels in matter and the transitions between them. And that led to semiconductors, it led to lasers, and so on. So quantum physics at that level was already transforming society. But what about some of these odder properties? At the time, one could only really do experiments on bulk matter, on ensembles. The idea that you could look at individual quantum systems took a while. Okay, and I can't resist the jumps and ichthyosauri. Okay, Schrödinger, back in about 1950-ish, said, we're not experimenting with single particles any more than we can raise ichthyosauri in the zoo. Okay, he felt that the whole quantum jump stuff was actually a figment of the imagination, not real. There's a quote you can see on the top. If all this damn quantum jumping were really here to stay, I should be sorry I ever got involved with quantum theory. Okay, well, just to reassure everybody, quantum jumps are real. Okay, and in particular, you can start working with individual quantum systems. And one of the revolutionary developments in this was the ability to trap and call individual atomic ions and look at the fluorescence from them. And what you see there, on the left-hand side, is an array of ions, and in the middle, looking at the fluorescence. And those individual ions then act as a kind of atomic telegraph, almost like a lighthouse flashing on and off as it jumps between a fluorescent state and a non-fluorescent state. And it's the heart of the development by many people, including Patrick Gill, I can see in the front here, of ways in which this could be used for new optical clocks. Okay? Right. So, jumps are here to stay. Just to show you this is from my friend Rainer Blatt in Innsbruck, where you see you've got this transition between the S state and the P state in a trapped ion. Fluoresces like crazy. You make a transition to a D state, which is metastable. It stops the fluorescence. And then you can see this jumping between on and off. Okay? It really is an atomic telegraph and is the key to an awful lot of what we do. So, quantum jumps, Schrödinger was wrong. Okay? It's there, it's doing stuff. Right, now let's think about entanglement and then the paper by Einstein, Podolsky, and Rosen, where he thought that he'd found a way of demonstrating quantum mechanics was incomplete. Okay, there is Einstein, Podolsky, and Rosen, and the concept was of two entangled systems separated, where you observe one and you can deduce something about the other. The phrase entanglement was actually very much Schrödinger's. Okay, that's the abstract from that. I love the way it was communicated allegedly by Mr. Born, because of course Cambridge didn't recognize the German degrees of Max Born. Okay, so he is Mr. Born, according to Cambridge. And he communicated, and that's basically the restatement of what I showed you earlier about the fact that, and I want this one to be stressed. It's the characteristic trait of quantum mechanics, the one that enforces the entire departure from classical lines of thought. By the interaction, the two represented by the psi function have become entangled. Okay. Now, entanglement was very much something that theorists used to play with, but it was actually our next character on our list that I think is worth stressing, and that's John Bell. And John Bell was able to show that there really are things that you can do now that demonstrate the oddity of quantum entanglement. And so he came up with an inequality that could be tested experimentally. Okay, so there is John Bell scribbling on a blackboard on stuff. In the middle is my friend Alan Aspey, who actually did really convincing experiments on demonstrating the Bell inequalities. I love the way that a physics theorem has a street named after them. Okay? It's not Bell's Crescent, it's Bell's Theorem Crescent in Belfast. I think that's a lovely idea. Now, if we start playing around with entanglement, let's look at some of the key ingredients. And there are two key ingredients that we need to stress, and that's Alice and Bob. Okay? You can find your own pictures of who is Bob and who is Alice, but these are the ones that I like anyway, and a lot of other people in the room also like. So there's Alice and Bob, and they're going to be exchanging information and measurement results between each other. And in particular, what you can do now is you can have two quantum bits, qubit 1, qubit 2. You can then start to interfere them in a way, and this picture on this side talks about the polarizing beam splitter that does it, and two detectors. And what you can do now is to do Bell state measurements which measure the correlations between the two components. And that's a key ingredient of a lot of what we want to be able to do. Having done that, you can now do teleportation. Jianwei Pan, who will be speaking, I think, online tomorrow, that was his PhD thesis, demonstrating teleportation, where one has a source of correlated photons, EPR photons, Einstein, Podolsky, Rosen correlated photons. You do another quantum comes in, separate to that. You do a Bell state measurement, and you can move that quantum property over to Bob, and that's now a teleported state. Better than that, you can do what's called entanglement swapping. Now I'm going to move away from this microphone because I need to point to something. Now I have two correlated pairs of quantum particles. I'll do a Bell state measurement here. That was correlated with that. That was correlated with that. You do a Bell state measurement, and now there and there, which have never met and did not come from the same source, are now entangled. That's entanglement swapping, another key ingredient. So with all this activity, how do our pioneers get recognized? Well, there's a plethora of Nobel Prizes. It goes back a very long way. I've picked out pictures, mainly for the people that I've either met or run into over the years. And these are the people that have transformed the way that our scientific understanding of quantum matter has developed. And right at the top, on the right-hand side, Alan Aspect, John Clauser, Anton Zeilinger. On the top left, that's Serge Roche and Dave Wineland. In the middle, the laser cooling pioneers. And then at the bottom, two of my heroes, one of which may not be known to many of you. On the bottom left is Alfred Kastler, who got the Nobel Prize for optical pumping. I'm in my 7th decade of worrying about quantum. In 1967, in Sussex, I was doing optical pumping experiments, measuring the decoherence of Rabi oscillations. Kind of desperate that I'm still worrying about it. And then that's Rabi on the other side. Okay, right. So you've got this business now. The everyday world we see is classical, and the microscopic world is quantum. So what's quantum, what's classical? And in a famous Physics Today article, Wojtek Zurek produced this cartoon of a kind of barrier between the quantum world and the classical world, where on the right-hand side, everything is sharp and determined, and on the left-hand side, things are really fuzzy and indeterminate. Okay? What's classical? What's quantum? Now, this is my personal opinion. There is no such barrier. The barrier between classical and quantum is determined by how much money you've got. Because if you have exquisite experimentation, you can follow through the correlations. If you don't, you lose those correlations, and you're back to the mixtures that we see in the everyday world. So, if there are any bankers present, help us overcome that barrier, okay? And of course, that was shown experimentally by the two figures that I've got here. Herbert Vater, who sadly died before he should have gotten a Nobel Prize, in my view, and Serge Roche, who showed that even the most classical of electromagnetic field states has a quantum property. It's discrete. They see the lumpiness of the field. Right, so we got these funny quanta, photons. What can we do with them? How about trying to beam split one? So we've got a collection of people here. Okay, that's John Clauser up on the top left. John did share the Nobel Prize with Aspect and Zeilinger. He'd pioneered these experiments at Berkeley. Okay? He didn't get tenure at Berkeley because they said, you're just testing quantum mechanics. Everybody knows it's true. What a sad story. Okay? So that's John. Alain, top right-hand side. Philippe Grangier, next one down. And then I spent 3 very happy years working in Rochester, where the office mate next door to me was Leonard Mandel on the bottom right-hand side, and Jeff Kimball. If I take a quantum, a photon, let's see if we can beam split it. Okay? Well, you can. Okay, so I'll take a single photon, a beam splitter, and say, do I get a click here and a click there? Can I split a photon? Is it indivisible? That's the experimental apparatus. Okay, you've got a trigger to set the electronics going, and then you have a go at beam splitting a single photon. And what's the outcome? You find that you get anti-correlation, sometimes called anti-bunching. So there's a funny quantum domain down there and a classical domain. Those of you not specialists, let me tell you why you should be horrified by that experimental outcome. It violates the Cauchy-Schwarz inequality. Okay? It tells you something about the average of the square of the intensity compared with the square of the average intensity. It violates the Cauchy-Schwarz inequality, which means this light cannot be described by classical probability, which is positive everywhere. All right? Now be horrified. Probabilities that aren't always positive. Okay, take-home message, be horrified. Right, so I'm going to skip that one because the video doesn't play. So now what we've got is the individual quantum systems we can play with. We've got the instruments to do it, laser cooling. We've got lasers around. We've got all sorts of ability to control at the microscopic level. All right, so now we've got the second quantum revolution, which is exploiting all of this. Okay, I'm going to start by saying the first people to exploit coherent superpositions experimentally were Essen and Parry at NPL, who showed that you could build an atomic clock where you could put atoms into superpositions that precess. That precession frequency is tremendously well determined and formed the basis of atomic clocks. It formed the basis of our time standard eventually, and then, of course, atomic clocks in space led to sat-navs. And every one of you, both online, I guess, and here in person, have used those atomic superpositions to navigate your way to this building. Okay. Well, what else can you do on it? Now, the problem simply is these superpositions are fragile. They engage very well with the environment, okay? And it's the enemy of what we want to do in quantum computation, but it is our ally when we're trying to sense the outer environment. So what sort of things can we look at? Now, this is a slide we use quite a lot within the UK program, a whole raft of application areas. And then people talk about computing, communication, and sensing, and look at the predicted market size by 2040. And now here's the horrible warning. Computing between 45 and 131 billion. When you get error bars that enormous, it's our duty to close those error bars down and to give a little bit more likelihood to how we're going to transform what's going on. Okay, quantum computing predicted by 2035, the value to be between 0.9 and 2 trillion. I mean, we need to sharpen that one up. So, who's doing it all? Well, here's the investment profile in terms of government commitment to quantum around the world. Okay, so on the left-hand side is the China spend, and both the low and the high number, because there's a degree of uncertainty in quantifying what the spend is. Okay, the next one down is the US, then the UK, and so on. There's one, oh, no, we don't want to do that yet. There's one just here, which I think is great fun, where one nation doubled its commitment overnight by persuading a foundation, Novo Nordisk, in Denmark, that quantum was going to be really of value. And that was the Novo Nordisk intervention, which doubled the Danish appetite for quantum. Right, the UK program. How did it start? We did a meeting at Chichiley Hall, which was a Royal Society venue, and we gathered together people for a few days to work out what we could do together that you could not do separately. Who in the room was there? Put your hands up. Thank you. I really missed Chichiley. But it enabled us to demonstrate that by collective action, we could do something. And then we persuaded the UK government that this was a goer. There was investment in the first 5-year phase. We had this idea of research hubs. There were 4 research hubs. Some of the directors are in the room. And they were working altogether, 30 universities, a lot of industry. The second phase, another 5-year phase, where the big change was keep that pipeline of discovery going, but start to engage with industry. And the Industrial Strategy Challenge Fund was transformational in this, in working on ways in which we could work with industry on industry-led projects to demonstrate the capabilities that quantum will give. And then over a year ago now, we developed the quantum strategy about where should we be going in a 10-year period with our investment in the UK on quantum. So what did we do? So if we look back 10 years, so I'm not looking back 100 years now, but just 10 years, we spent 1.1 billion of public money on this new model of working together. 44% in terms of research, and the heroes there were EPSRC, and to some extent later on, STFC, but very much EPSRC leading the charge. Innovation with what was then called the Technology Strategy Board, and then became Innovate UK, and other government departments as well. We put 22% in terms of spend on infrastructure. That involved building the beautiful AQML at NPL, but also the National Quantum Computing Centre at Harwell. And 9% on skills. That skills part is now expanding quite a lot. Now, what do we do with it all? Real world stuff. Okay, real world stuff that affects people's lives. Top left-hand side, if I take a miniature atomic clock with atoms in superposition, it can measure magnetic fields exquisitely. Okay, well, I could use that to measure the magnetic field when a neuron fires. Okay, now I'll build an array of these things and generate a functional brain imaging. And that came out of Nottingham University, commercialized with Circomagnetic, is already being used around the world by surgeons treating juvenile epilepsy. Okay, then we can look at a whole raft of things involving space, where very much University of York has been leading that charge. We can use single photon cameras using SPAD detectors to detect greenhouse gases. And again, a startup from Bristol, QLM, is doing a wonderful job on that one. We can move information around the city, where quantum mechanics will do something about the ability to detect intrusion on this one. And that's been pioneered by British Telecom, Toshiba, and HSBC around the data centers and the financial sector in the UK. Bottom middle, how do you interface quantum devices with data centers? And on the right-hand side, what's under your feet? Using gravity sensors, atomic interferometers, to develop what's going on around you. Okay, so what have we done in the UK? We've got these areas, quantum simulation and computing. We've got quantum networking, quantum sensing, imaging, and timing. Right in the center, the industry-led challenges, and on the top right-hand side, the National Quantum Computing Centre, which opened last autumn on the Harwell campus, where we have test beds, we can work on quantum readiness. That's led by Michael Cuthbert, who is sitting over there. Okay, thank you, Michael. And that's going to be our bridge between the research and the scaling and getting on with this at substance. So that's our program. And here's the take-home message from our program. It ain't just computing, okay? There's a whole raft of things that are having an immediate effect. Quantum sensors, and I've talked a lot about that already, and I don't need to go through all that list. That's where there's some immediate returns in quantum sensing, okay? And I've given you some examples, and I'll skip through that one. But, you know, global navigation and timing is actually the way in which you might want to see an immediate connectivity with the general public, because that's what they use all the time, okay? So when we're doing our ambassadorship with the general public, do stress to them that atomic clocks have this beautiful quantum superposition property, and it's enabled, and you can see it in your phone, okay? Right. Sadly, the world is not rosy in terms of GPS, okay? It's dead easy to jam. It's dead easy to spoof, okay? And if you do spoof it, London Economics showed the economic impact of a disruption to GNSS is 5.2 billion over a 5-day period to the UK. So on the top right-hand side is the Government Office of Science Blackett report that we did on GNSS vulnerability of the economy. Who in the room helped us out with that? Yeah, small hands went up. Okay. Sometimes Patrick Vallance and I have called this the Sisyphus Committee, because keeping it going has taken forever. I led the work for the Cabinet Office and so on, and it's finally now being resolved through the National Timing Centre work led by the National Physical Laboratory, where we need to do it. Now, quantum computing. Our hero, in the UK at least, okay, David Deutsch. I've known David now for 40-odd years. I've never seen him in daylight, by the way. But it was David that came up with the first non-trivial algorithm to demonstrate that you could do something on this one. And why does it matter? Well, it's a phrase I probably I probably advanced in its stupid phrase. I wish I hadn't. The crypto apocalypse. What a quantum computer does is it changes its complexity classes. What was thought to be really difficult, in other words, non-polynomial in terms of resource, becomes easy, i.e. polynomial. And that's right at the heart of what was going on with Peter Shor's algorithm. But that hardness assumption underpinned everything we do in terms of our internet protocols, TLS, RSA, and so on. And so all of our encryption primitives need to be retooled. The best estimate is a cryptographically significant machine might be 10, 15 years away. But the trouble is, retooling the cryptographic primitives will take 10, 15 years. So we have to work hard on it. What gives me confidence about quantum computing? Okay. Well, I've pinched this from Steve Brierley from River Lane. The quality of the quantum bits has got better and better. And the number of quantum bits is increasing. But size isn't everything. But you need to be able to correct on errors. And I think the revolution of the last 12 months has been quantum error correction is now. All right, so my final slide, because I'm about to be hoiked off by Martin. I think what we've demonstrated is great research turning to economic and societal value. Going back a whole 100 years, if you want. But the second quantum revolution has done that too. All around the world, people are working on it. It's not just quantum computing. The ambition in this space is good. To be bold is important. It is the International Year of Quantum. Take part in it. Thank you for listening.
Well, thanks very much, Peter, for that tremendous overview. Just before we get to the question and answer session, a couple of things to mention. There is a big timeline chart just where the cloakroom is for those who've brought coats and seen that, courtesy of the University of Bristol for those who are attending in person. So please do take the time to look at that. It really lays things out in detail. And also at lunchtime on screen, we'll be showing some summary of the quantum pioneers that Peter mentioned during his talk. So please also have a look at that. We want these sessions to be as lively as possible, so we very much encourage questions and comments from the audience who's here in person, but also online. There's the Slido link for online questions. But after that tremendous overview presentation by Peter, we'd now like to open it up to the floor, please. Any questions and comments that you might wish to raise. So please help us make this a fully interactive session.
Peter, Simon Harwood from Leonardo. Thanks for an excellent opening speech there. My issue is one, for those that don't know, we're a defense company. So we're early adopters of a lot of technology, putting them on planes, satellites, subs, etc. And as I look at the spectrum, you know, we're moving quite quickly in the adoption of this technology. And obviously the science and technology on the left-hand side, as you indicated in the speech, has been going for many years and it's at a very high level. The challenge I've got, I know it's a bit of a misuse of the term from DCIT and DBT about technology adoption, but the main issue I've got is the supply chain, the industrial supply chain, building the various components and aspect in the middle. So I guess my question is, how do we here in the UK encourage the middle bit, the technology adoption, the UK supply chain, to take the excellent science so that I can embed it on those plane, ships and submarines that we need to do?
That's actually at the heart of what we're currently worrying about as we want to be able to deliver the missions. Okay, we have these 5 quantum missions we're trying to deliver over the next decade. None of those are going to be possible without a resilient supply chain. Where do you get the materials from? Where do you get the compound semiconductor stuff? Where do you get the VCSELs from? Where do you get the sources? Where do you get the SPADs from? And so on. All of this is right at the heart of what we're trying to do at the moment. We're not neglecting it. We therefore will have to work in an international environment to make sure that that happens appropriately. But there are people in this room who are working really hard on the way that we move from looking at components that are robust, well-engineered, into product. I mean, I see Jen sitting there right in the front, who's been at the heart of what we've been able to do up in Strathclyde on components that are really important for this one. There are others in the room I could point out as well. It's not easy to do it on your own. So the UK is fragile if we don't engage with the rest of the world on this one. You know, where do we actually get some of the chips manufactured, for example, is going to be important for us. We have some thoughts on it. We do not have a chip act in the same way that the US or Europe have at the moment. So it is a concern. Supply chain is the heart of some of the things we worry about now. You're quite right. So if you're a defense company with an Italian base and a massive Scottish investment, you want to make sure you can make stuff that you don't have a single point of failure because you can't get stuff out of one particular country. Okay? So, yep, you're absolutely spot on. No quick fixes on it, though, I'm afraid.
Peter, I was very impressed by how quickly, how concisely and clearly you summed up the genesis of quantum mechanics. I wondered, in the light of what you said, whether you felt there are any aspects of the foundations of quantum mechanics that still remain to be understood. And if there are, do you think that resolving them might lead to yet more applications?
Yeah. One of the things that we have not yet got is a marriage between quantum mechanics and general relativity, by the way. They're kind of almost incompatible. So looking at the way that gravitation and quantum mechanics marries up together is a big challenge. And there are people in this room, I can see Myung-Shik Kim, for example, is worried about these things. You know, do we have a fundamental theory if we don't have gravitation involved in it? So that's one. The other part of it is, what the hell is the universe made of? Well, dark matter, but what is it? So that's why we have down at the Bulby mine, an underground laboratory. I think it's a good idea to send undergraduates down there. It's a mile down, looking at dark matter. So, yeah, look, the journey's not over. The journey is not over. Most of the universe, we don't know what the hell it is. And in addition, we've got to find a way of marrying up general relativity and gravitation with quantum. That journey is underway still. Wait for the microphone, because people online won't hear you.
Hi, Carl Savage from STFC. We've spent quite a considerable sum of money getting to where we are today in order to give us a resilient supply chain so we can get the benefits of the full benefits of quantum technologies. Do you see it as requiring a higher level of investment, or is it simply a matter of time that volume of production will drive the supply chain?
I think for the work on sensors and timing, we have the right degree of support. Venture capital has worked quite well on that one. The companies have evolved. They start to work now with the primes and the integrators. So I think the sensor side of it, I think we're in reasonably safe hands, notwithstanding our Leonardo colleagues' comment about the supply chain. Quantum computing will require state intervention. And the reason is that it's a long journey, and venture capital will want an exit faster than that unless we find some way of inventing patient capital. And that's the tricky bit of how do we get on this long journey, a 15-year journey, towards a large-scale fault-tolerant machine. That will require state partnership with the investor community. We are looking quite closely at what happened in Canada with the transformation of the pension rules on investment in technology. But we have to do that because it's a long journey. The state will always play a role in computation, in my view.
Hi, Richard Harding from the Hartree Centre, and I'm a quantum numpty, so bear with me. As I'm outward facing and liaising with industry and I look after healthcare, for example, and I start to think about sovereign infrastructure, and I think the stuff Michael's doing at NQCC is brilliant. We're working with PsiQuantum and Quantinium and IBM. Do you have a sense of when we're going to get some of this sovereign infrastructure in the UK? Because there's a sense nervousness from some of the public sector people that we talk to about when that's coming?
I believe we've got, through the testbed program, already the ability to actually start to get prototype machines where we can kit the tires in the UK. If you look at some of the UK companies and the way that they're expanding, they have that ability to do stuff in an interesting way. So I believe it's still too early to find a winning platform on this one, by the way. I think down selection is going to be important, but not yet. And the reason I say that is that some of the platforms are now showing more promise than they did 5 years ago. For example, neutral atoms are now looking terrific in this space. If we'd have down selected 5 years back, we would have made a mistake. Okay? So Quera have invested into the UK in substantial way. Inflection, alias Cold Quanta, which Dana over there founded, has a major investment in the UK. We will have sovereign capability. It won't necessarily be at a monster scale immediately, but we'll get there.
Thanks, Peter. I think in the interest of time, we should draw this part of the programme to a close, but we should all thank Sir Peter again for a fantastic... So we're straight into the next session now, which is on hybrid quantum classical computing. Ellen Kashefi, who was originally due to chair this part of the program, couldn't be with us. And we're very grateful that Ellen Devereaux has stepped in at the last minute to the hot seat, and she'll lead this session. So thanks very much, Ellen.
Thank you for the introduction, and thank you for having me here today. I'm Ellen Devereaux. I'm a quantum computing consultant at Fujitsu and a full-time PhD student in quantum algorithms. So I'm really excited to hear about what our speakers are going to speak on hybrid quantum classical computing. We've got 2 talks in this session today and then a Q&A session at the end. So first up, we've got Professor Andrew Daly from the University of Oxford discussing the quantum advantage in quantum simulation.
Great, so thank you very much to the organisers. It's a great pleasure to have the opportunity to speak at this meeting. I'm very excited about the discussions we're going to have over the next couple of days. Of course, it's very difficult to follow such a great introduction to the field as Sir Peter has just given us. But I wanted to go into a little bit more detail on the sort of perspectives of kind of where we are and where we're going at the moment with quantum computing and quantum simulation. what some of the near-term opportunities are. And so what I'd like to do is sort of illustrate the sort of fact that when we sort of ask the big question of when are we going to be able to do something that we can't do on a classical computer, that for certain sort of specialized problems in science, the answer is already now. We have, for scientific purposes, in certain cases, advantages over classical computing. And of course, the next stage question is then, well, how do we start to make use of those, and how do we sort of really sort of have an impact that goes beyond just basic science? Of course, some of that will come as we scale over the next 15 years to these large-scale sort of fault-tolerant machines. But it's interesting to ask what we can do sort of in the near future, in particular by asking about the connections with classical computing, hence the sort of hybrid sort of classical quantum. And one of the big questions in that is going to be to understand where the places are that are most promising for quantum advantage, understanding exactly what it is that we can't do on a classical computer that we can on a quantum computer. So what I'm going to do is sort of talk about this question of where we are, what we can do both with digital quantum computers and also with analog quantum simulators. I'll explain sort of what we mean, where we are, and where I think we're going. So I and my group are currently in a sort of classical superposition. I moved 18 months ago from the University of Strathclyde in Glasgow to the University of Oxford, and we have about half the group in Oxford at the moment, about half the group in Strathclyde. You'll see we managed to find sunny days both in Oxford and at Strathclyde in Glasgow for our group photographs. And so we're theorists with a background in many-body physics and in quantum optics and open quantum systems, sort of asking now what the sort of near to medium-term architectures and applications are going to be to get advantage out of quantum computing and simulation. And most of what we've done has been inspired by the developments over the last 20 years, and especially over the last 5 years, in controlling sort of individual quantum systems and building up to these sort of scalable quantum computing regimes. And it's really interesting to think, back to the quote that Peter noted in his talk, where Schrödinger said that, we can't, thinking of dealing with an individual quantum system would be like sort of raising ichthyosauria in the zoo. Well, now with with neutral atoms and quantum gas microscopes, we have about 10,000 ichthyosauria that are controllable now on the level of single atoms and single lattice sites. And as we sort of go to the right on this sort of chart of machines in which we can do analog quantum simulation and indeed digital quantum computing, what we're sort of seeing is that we go to sort of thousands of atoms now with neutral atom tweezer arrays and hundreds of sort of superconducting qubits, also well over 100 trapped ions in some of the new 2D setups and around 50 odd in the one-dimensional setups. And again, with this sort of level of microscopic understanding and control over these sort of individual components that make up those systems. And what is particularly interesting for me also is this combination we can now make where some of the systems where we have used them as analog quantum simulators are now also being used as digital quantum computers. And people, particularly in the last years in tweezer arrays, superconducting circuits, and trapped ions, have been combining these sort of modalities, using digital operations to prepare states, using digital operations for readout, but using the natural Hamiltonians of the system in the middle to generate quantum entanglement, to generate useful resource states, or to do sort of computations that are interesting for many-body physics. So we're starting to see many-body physics being done in this sort of hybrid analog-digital mode, which I think is going to be very fun to explore over the next couple of years. And I'll say more about that over the coming slides. So what are the sorts of problems I'm thinking about when I say we have some quantum advantage now for specialized cases? Well, what I'm focusing on here is the challenge of many-body quantum systems. And this challenge of understanding and controlling many-particle quantum systems goes back now half a century to different problems in solid-state physics. And we can think about sort of questions in problems that are relevant to physics in the solid state, relevant to high energy physics, relevant to questions in quantum chemistry, and then ultimately also the sort of interacting many particle systems are relevant to electrons as we try to design better battery cathodes or industrial catalysts. They're important when we try to solve quantum chemistry problems for drug discovery, and they're important also when we think about designing sort of how we use and program quantum computers and other types of quantum technologies. So these are also, in a sense, really real-world problems. And in many cases, in particular in the solid state and in chemistry, we lack the understanding of the underlying processes in interacting quantum systems, and even the simple models that we would like to write down are not tractable on classical computers. And so this is where we hope that quantum simulators and quantum computers are going to make a big difference. And so there are two modalities that we can think about, sort of especially in the near term, but elements of those I think are going to go over a longer time period as well. And the first is we build a quantum computer and do a digital quantum simulation. And that way we sort of program the models we want to solve on a digital quantum computer. We have the flexibility that we can program something close to the models that we would like to describe real materials. And going forwards, as we scale these machines, we have error correction, which means that we can also solve these models with the precision that we would like if we're willing to trade off the fact that the computation is going to take longer and require bigger quantum computers. The challenge is that at the moment we're still in the process of scaling to the sizes that we need to beat classical calculations. And again, I'm going to take an example and look at that in a moment. The other option is to work with analog quantum simulators. And here what we do is we take a quantum simulation with, for example, cold atoms here and optical potentials. We build the model that it is that we want to solve. And then we observe what happens in an experiment and by directly studying it, get out hopefully information that is quantitatively accurate and that we can't calculate on a classical computer. The advantage is that we already have some systems where we have up to 10,000 particles, which is much larger than we can calculate classically. The downside of an analog computation is that we have calibration errors that directly lead to errors in the final computed values, so we don't have this ability to directly do error correction in those systems. So the question that we might want to ask then is, when can we expect then to see quantitatively accurate solutions in regimes that we can't calculate classically? And to think about that, I'm going to take an example with a model we can build with cold atoms and optical lattices. That is the Hubbard model, which is sort of a workhorse of strongly interacting systems in solid-state physics. And in particular, when we study those models sort of out of equilibrium, we find that we get to situations that are very difficult to calculate classically. At the moment, if we start with an initial array of particles in a lattice, this model was originally written down to describe electrons, but now describes on a microscopic level atoms and optical potentials. Then the best classical methods that we have to simulate those are methods based around tensor networks. And what we find is that as we try to evolve the system in time, for sufficiently large systems, we need essentially an amount of resource in terms of the computation time and the size of the computer we need that grows exponentially with the time scale over which we like to simulate these models. In some cases, we can make this easier if we don't have fully coherent dynamics or if we have homogeneous systems. But for a lot of transport problems related to electrons when you're designing sort of materials for battery cathodes and things like that, we have problems that are then very difficult to solve classically, and where if we go beyond certain timescales, the errors grow exponentially. We should compare those errors then in our calibrated classical calculations to what you would get if you tried to solve this with an analog quantum simulation. And what we can do, particularly for atomic physics-based systems like trapped ions or cold atoms and optical potentials, is write down microscopic models that describe not only the dynamics we want to look at, but also the error sources, the decoherence, the noise in those systems. And there what we find is that at short times the noise is dominated by calibration errors, at long times it's dominated by decoherence, by spontaneous emissions. And we can put in numbers from current experiments and see where we are with respect to current classical techniques. And what we find there is that the classical techniques, after some point, they're very accurate, but then we require exponential resource to avoid an exponential increase in the error. Whereas these analog machines can reach a regime of advantage over those classical calculations, where on some time scale, they can simulate dynamics that are very difficult classically. So we have an advantage over the classical simulation, and we have quantitative accuracy below the percent level using all of our understanding microscopically of current experiments. So we're in a regime there of quantum advantage. If we can build a fault-tolerant digital quantum computer, we can do in principle even better and improve that error scale. But the question is, what resources do we need for that? And so what we can do is we can go through and analyze what resources we need. And to beat sort of current calculations, if you sort of start with of the order of sort of a 10 by 10 lattice, which is what people can control quantitatively, in these sort of Hubbard model experiments at the moment in analog quantum simulators, and which is clearly beyond what we can do on a classical computer, then what you find is that you need of the order of about 100,000 gate operations on a digital quantum computer. And what this means is that clearly it's beyond what we currently expect in the NISQ era of quantum computing. So we have the potential for quantum advantage in analog quantum simulation. It's beyond the NISQ era, but what's actually exciting is that at the moment, there are now roadmaps over the next 2 to 3 years to scale the digital quantum platforms, for example, in superconducting qubits and neutral atoms, with also others sort of hot on the heels, to of the order of a few tens of thousands of qubits with error rates of the order of 10 to the minus 3. You can then do at least 1 or 2 layers of error correction and get down to this few hundred qubits at these sort of 10 to the minus 6 error rates that you might need to have advantage also in the early fault-tolerant era. So that's exciting, with the next challenges being then to identify how to take this quantum advantage for science and make it useful in chemistry or materials. What's going to be vital is to work with experts in those areas to understand where the windows of opportunity are also in the near term, to develop hybrid quantum and classical algorithms, understanding which parts of calculations you can do on a classical computer, where these quantum machines with some quantum advantage will be useful as coprocessors, and perhaps look to use them to calibrate or test approximate classical methods, or maybe potentially even train classical machine learning algorithms. And I think the future of these things, generating information when you are in these regimes that we can't calculate on a classical computer, is going to be very exciting. There are a number of other things that you can do which are of importance scientifically and wider in quantum technologies, also with analog quantum simulators. A number of these systems, for example, by moving atoms in tweezer arrays, allow you access to longer range couplings. And this is exciting because it means that even if you can't do error correction, that this relevant size of entangled resource states that you can build can grow exponentially with the coherence time of the system. And so what we have understood in recent years is that these long-range couplings can sort of fundamentally allow you to build bigger resource states. What's very interesting is then to think, for example, about how you might use these entangled states. As Peter said, it's not just quantum computation, it's also other types of quantum technologies. Can we feed in these resource states to build, for example, better atomic clocks, better ways of doing quantum metrology? Another example of the connection between quantum computation and classical computation is that these tensor network methods that are the best methods we have currently for quantum dynamics, we and others have realized in recent years that you can now apply those methods that were designed for describing quantum systems actually to solve large-scale problems in partial differential equations. And there's a lot of interest now in applying those, in particular, to computational fluid dynamics, another very challenging problem computationally, and to plasma dynamics. So this is another way that we get crossover between the development of quantum computing and the development of classical methods, and the interaction between these, again, understanding where you make use of the quantum advantage, I think is going to be very exciting in the next few years. So in summary, the outlook for programmable quantum simulators and for quantum simulation with quantum computing, I think, is very exciting. We're already at the point where we're looking at new sort of fundamental many-body physics here, in particular in some of these long-range coupling models and potentials to study what we call fast scrambling in many-body systems, building up entanglement very rapidly. And there's a lot of potential to uncover unexpected phenomena that would be interesting to basic science. The next step here is going to really involve a lot of interaction that's already happening through the quantum hubs, through industry-academia collaboration, and in industry in general, connecting to these problems in materials and chemistry, understanding where the windows of opportunity are, where you can make a real difference with quantum computing also in the near term, and perhaps thinking about other applications like quantum metrology. And I think with this sort of path towards sort of error correction in the early fault-tolerant era, and also the sort of spin-offs of quantum-inspired classical algorithms, we're in a very, very exciting time for the development of quantum computing. I think it's a great time to have the International Year of Quantum and to think about the real-world applications of these things going forwards. Thank you.
Thank you very much, Andrew. We'll take questions after the next talk. So next up we have Professor Crystal Michelson from Forschungszentrum Jülich, who's going to tell us about embedding computing in a HPC environment, and that talk, I think, is going to be online.
I first would like to thank the organization for the invitation. I'm really honored. And I regret that I cannot attend personally, but this is because of family circumstances, unfortunately. So I'm first going through the potential applications of quantum computing. So in the previous talk, we already have seen that there might be advantages in physics simulations, but there are also promising applications in our daily life. And one can think here, first type of applications are all kinds of optimization problems. And we know we have many of them. We have optimization in supply chain logistics, and something that we experience in our daily lives is traffic. We all would like to have this traffic to optimized in a good way, or at least in a better way. Energy grid management is another of such optimization problems. If we talk about optimization, then we can also talk about machine learning, because optimization is part of machine learning. And if we can bring machine learning to the quantum computer, then we can use it to analyze picture and study, for example, climate change. But we can also use it to study the human brain functionality by looking how the neural networks behave. And as we have seen in the previous talk, we have applications in physics due to simulations. But with these simulations, we can also work on materials design. And from materials design, we can also go to the chemistry, quantum chemistry, and do some drug design. But our vision for a long time at the Jülich Supercomputing Center is that in order to go to this practical quantum computing, we will have to combine high-performance computing and quantum computing. So we really have to combine the best of both computer technologies. The reason is, at least for now, our quantum computers are small, they are not ideal, and they are also not universal. Even the gate-based quantum computers are not universal. So they will be good for particular problems, but in order then to expand their applications, it's best that we combine them with our classical HPC systems. So in Jülich, we have high-performance computers that have a modular architecture. And this means that they consist of different modules, which in principle can be independent machines, but can work together through a software connection. So usually we have a cluster module, which mainly consists of CPUs. We then have another module, which mainly consists of GPUs. And then we have some other modules for data storage and data analytics. And we reserved, a while ago, modules, so to speak, for quantum computing, but also for neuromorphic computing, which might be another future compute technology. Now, this modular architecture allows us for a tightest possible integration of quantum computers into this HPC environment. And actually, this modular architecture is ideal for integrating the quantum computing capabilities into our standard HPC workflows. So one example is if we have these big codes for simulating climate and predicting weather, maybe, and this is a challenge for all programmers, maybe there is, for now, already some part in this big code that can be given to a quantum computer so that the quantum computer can carry out this task, give the results to the HPC system so that the HPC system can continue with the result. Will this have an advantage? Yes, maybe not in speed, but it will definitely have an advantage in energy consumption. At GSC, we have a quantum computing strategy which consists of 4 pillars. The first pillar is emulation and modeling quantum computers for which we need these big systems. This I will not discuss here. Another pillar is the integration, which I discussed before. And a third one is the provision strategy. If we want to integrate these 2 types of computers, we need to host also quantum computers. And we started with this in 2022 with a D-Wave quantum annealer. Why? This is an analog quantum computer which has more than 5,000 superconducting qubits. So this allows us to study some prototype applications. And it was available commercially, which gives us a certain guarantee that this is not an experimental system, that one can use it 24 hours and this 7 days a week. And this also turned out to be the case. Then we thought, okay, we can also go to another analog system, and that's a quantum simulator, which we get, or which we have become delivered by a French startup company, Pascal. So this is a quantum simulator with neutral atom qubits, and it has more than 100. The system is at the moment installed, and it's calibrated, or the calibration is going on. So we hope to have our first users on this system in the summer of this year. But of course, we are also interested in the digital quantum computers. And we have several projects in which we acquired such a system, hosted, and plan to integrate it in our HPC environment. One of them is a trapped ion system. A first system will have about 30 qubits. Then later on, we will have one with 60 qubits. And this will be delivered by Electron, which is a startup company here in Germany. We will also have a very small system with only 5 qubits, but this is a different technology. It will namely have semiconductor qubits. We can also proudly say that, of course, we also have systems with superconducting qubits, and in this case, not only commercial systems. So we have one commercial system installed, which is integrated with the HPC system, and that's a 5-qubit system from the company IQM. For the rest, we are working in national. QSolid is a national project, and Open Supercube Plus is a European project in which this type of systems are designed, developed, and then for this, a complete software stack is developed within the project. And we are then at the, let's say, user end, where we again integrate these systems in our HPC environment, which also contains the other quantum computers. So in order to do this, we have established a quantum computer user infrastructure, which is called UNIQ. The role of UNIQ is not only to acquire these quantum computers, install and provide them to the users. What we also do is we develop algorithms and prototype applications, usually this together with our users, our customers. And we have a long tradition in high-performance computing. There we know it's essential to provide users with services, training, and user support. We also do this here, and we pay special attention to this hybrid use of quantum and classical computing. So what do we have? Of course, at the heart, we have our modular supercomputers. We then also host the emulators, which I did not discuss here. Then we have our analog quantum computers. We have the digital quantum computers, and the way that our users can access them is by a rolling call for peer-reviewed access. So users have to write a small project proposal, which is evaluated by external, international experts. And if the project is granted, our users have access for 1 year to the system that they have chosen. Not yet all are included into this rolling call, because this is a step-by-step process. And as I mentioned before, to some of the experimental prototypes, we provide cloud access, because we cannot allow ourselves to have a lab next to the computer systems. So for the analog quantum computers, we have built a special building because the DWF quantum annealer is quite some sensitive machines. As many of the quantum computers, temperature has to be controlled, vibrations have to be controlled, and so on. So in this building, we have 2 rooms. One is occupied by the DWF quantum annealer, and the second one is occupied by the Pascal quantum simulator. The other quantum computers are installed in another building at the Jülich Supercomputing Center. Let me go to one application. We have several applications, but I want to mention this one because this is in collaboration, or it has been done in collaboration with a company which belongs to Boeing. What we have been studying here was a tail assignment problem. So it's a hybrid quantum classical computing type of solution that we have, because we used quantum approximate optimization algorithm to solve it, We used also the DBF quantum annealer to solve it. And for the QIOA, we used our supercomputer. So what is a tail assignment problem? In this problem, one has to assign aircrafts to flights, this taking into account all operational constraints, and of course, we want to optimize the overall cost. This is a problem that airline companies have to solve several times a day. You have to take into account the working hours of the personnel, you have to take into account the type of airplanes you have, and of course, you also have to take into account what these airplanes are transporting. Quantum computers are small, so we have to simplify the problem and we have to make it smaller. We could reduce it together with Boeing to a problem which is finding routes to carry out 472 flights between airports so that the routes do not overlap. And this is a problem which can be solved on a 40-qubit quantum computer. We did not have a digital quantum computer with big enough size and a good enough quality. So therefore, we used our simulator running on a super computer. And we first used QIOA, and we looked at the success probability as a function of the number of qubits. So QIOA is represented by these green symbols here. So what do we see? We see an exponential decrease. When we observed this, we thought, oh, even if the quantum computer becomes bigger, this is not an algorithm that we will be able to use as such to solve these optimization problems. What did we do? We tried to find modifications to this algorithm in order to improve the outcome. One of them was the approximate quantum annealing algorithm. And you see we got rid of the exponential decrease, but still the success probability was not very high. And then recently we came up with another algorithm, which is the guided quantum walk. And this has quite a good success probability. So this is what one can do using these big HPC systems for quantum computing, for the applications also. As I said, we also did it or have put the same problem on DBF quantum annealer with more than 5,000 qubits. So that's a small optimization problem in this case. And there we found a success rate of 70%. So actually what users can do in Unique is also do this type of cross-platform benchmarking. One can use an annealer, one can use an emulator, one can use digital quantum computers and get a feeling for what these different types of technologies can do. Since this hybrid quantum HPC connection is so important for us, as I already mentioned, Pascal is acquired within the European project HPC QS, so High Performance Computing Quantum Simulator Hybrid. In this European project, there are two computer centers involved, one at CA in Paris and ours, the Jülich Supercomputing Center in Germany. At both sides, we have such a Pascal quantum simulator. We connect it to our HPC systems. And the nice thing is that with this computer center, we already have a connection between the classical systems. So at the end of the project, we will have a first federated hybrid HPC quantum computer facility in Europe. In this project, we use as a programming environment Captiva of Eviden. For the integration, we use Parastation Modulo of the German company Partec. We develop a full hybrid software stack going from libraries, benchmarking compilers to the cloud access. But we also pay attention to use cases and training. So it's a project which, so to speak, contains all ingredients except the one of designing and developing a quantum computer. As I mentioned, with UNIQ and HPC-QS, we will make this first European federated hybrid HPC quantum computing infrastructure. So with UNIQ, we actually started in 2019. Then HPC-QS started in 2021. The nice thing is that Europe also has been funding in 2022 6 other quantum computers, which are now connected to classical HPC infrastructures. And last year, Europe even funded 2 extra ones. And the goal of Europe is to federate all of them in one network for the European users. And this network has the name Euro HPC QCS. And with this, I would like to thank you very much for your attention.
Great. So if I could have Andrew back up on stage, and we'll keep Crystal online for questions now. If there are any questions in the room or online, and then just wait for the microphone to come round to give them. Yeah, go ahead and sit down. Got a question at the back there.
Andy Sellers from University of Southampton. I've got a question about the interrelations between quantum computing, classical computing, and artificial intelligence. So do you think quantum computing will accelerate the development of artificial intelligence? And conversely, are there tools within artificial intelligence that might be able to accelerate the development of quantum computing?
I can maybe give a first quick answer and then see if Crystal has a follow-up. I think there's a very important research questions that a lot of people are looking into now. I know, for example, also within our newly formed QCI3 hub in the 3rd phase of the national program, we have a number of theory and software groups thinking about not just quantum machine learning, but exactly this sort of interplay between classical machine learning and what you can do on a quantum computer. Asking questions whether you might be able to use data out of a quantum computer as a training set for classical machine learning. And so we very much hope that there will be this sort of interplay. I think it's very important also to note that in the application areas like quantum chemistry and materials that I was mentioning, machine learning is already playing a huge role. So we have to be thinking about the role of quantum computing really in an age where computation in those communities heavily does leverage machine learning.
Question. Quantum machine learning, yes. So also we have been studying this. First of all, on the quantum annealer, more recently also on the digital quantum computers. There are some of these machine learning algorithms which we have implemented on the annealer and which show a similar performance. The training samples are, of course, much smaller, so the problems that one can solve are smaller. So what we do is image analysis, so one has to then divide the image in many more small parts as we would do with classical machine learning, but this is possible. And this is a first step to these applications in quantum AI. It's not only for simulations in quantum chemistry and materials design. It, for example, also has very important applications for damage assessment. We can study land cover maps. And for example, if we had an earthquake or if we had a big storm, we can do a damage assessment without sending people to these areas there. That's something which is developed now for or with classical machine learning. And we are looking into whether also quantum machine learning can give some contribution there. Vice versa, can we learn something from AI for quantum computing? Probably yes, definitely. I think in the modeling and therefore also the design of quantum computers.
Probably have time for one more question.
Good morning, Manjri Chandran Ramesh, Amadeus Capital Partners. Particularly to you, Professor Daly. I was very interested in your CFD example, and I was wondering if you could just bring to life for me what would be enabled, in sort of a real-world use case with simulation, and then, if we were to achieve quantum advantage, what would that further enable?
So I think that's an excellent question. And of course, in any of these sort of classical facing problems, there's going to be, I think, a really interesting competition between new developments constantly in classical methods and developments in quantum methods. What's been happening just in the last few years is that some of these tensor network methods that people have been using to describe quantum systems, we've been using them to try to do simulations of computational fluid dynamics with very fine grid spacing. The idea is to represent the solutions in such a way that you represent it on a Hilbert space that would give you essentially an exponentially large number of grid points if you had a quantum computer in principle. But where you only need the solution on a much coarser grain grid. So imagine a turbulent dynamic simulation where you need to do the calculation accurately on very small length scales, but you only need to understand how that influences the behavior on larger length scales. And people have done a number of things. There are some very nice recent papers also, for example, out of Dieter Jarksch's group. Dieter's in Hamburg and partly in Oxford. And we've been looking at this for fluid dynamics, but also for plasma dynamics with various potential end users of these things. We're now at the point of, I think, really trying to compare what this completely new method gives us relative to classical simulations, but there were some very nice, very promising results out of Dieter Jarksch's group that were published recently, together with some of the experts in turbulent fluid simulation. If you could put these things on a quantum computer, we know as a variational algorithm that you would get a scaling advantage in principle over classical computation, but I think trying to find a better way to then translate this classical algorithm that came from the quantum world back into a quantum algorithm is, for us, the next research question. But we're excited about the potential there too.
I think that's all we've got time for in this session, so I've been asked to tell you that there's a coffee break now until 11:45, and then the next session starts at 11:45.
Thank you very much.
Hello? Is it on? Good morning, everyone. I'd like to start the next session, please. Okay, thank you very much. I'm Jennifer Hastie from the Institute of Photonics at the University of Strathclyde, and it is my pleasure to chair this session on enabling technology for quantum. So this session will have 3 speakers who will explore the enabling technologies that drive the development and scalability of quantum computing. So we're going to hear that classical computing continues to play a critical role, including for quantum error correction. We're going to hear about how the distinct properties of photons can enhance computational efficiency, particularly for AI applications, and how integrating quantum technology with AI and high-performance computing will be enabling applications across industries from energy and medicine to cybersecurity. There will be time for questions at the end of the session after all the speakers have presented, and those watching online are invited to submit questions via Slido. So it is now my pleasure to introduce the first speaker in this session, Dr. Steve Brierley of Riverland Limited. Dr. Brierley's PhD was in quantum information, following which he spent a decade in the intelligence community and worked as a senior research fellow at the University of Cambridge, leading major projects in quantum computing. In January 2024, he was awarded an OBE for his services to quantum computing. So today, he's going to tell us why quantum computers need huge classical computers.
Great, thank you. So indeed, it turns out quantum computers need these massive classical computers to run. So I'm going to explain why is that? What are these classical computers doing? Some of the constraints that make this a really interesting problem. And then I'll just briefly touch on some progress that's been made in this direction over the last few years. Since this is the Royal Society, a note to declare any conflicts of interest. So warning, I intend to make a huge amount of money solving this problem. So let's start with classical computing. Classical computers are essentially a bunch of switches. So transistors switch voltages from 0 to 5 volts. We've got very good at making them incredibly small, but this is how you implement logic on a classical computer. Right? You're flicking some switches. Quantum computers look quite different. So here are 2 pictures of 2 different types of quantum computer. On the right-hand side, you have an AMO system, so a neutral atom system in this case. But other systems like ion traps look quite similar. And on the left-hand side, you see a solid-state system, so in this case, a superconducting one. But again, silicon systems are going to look pretty similar to this. And I think what I wanted to call out is, we see these pictures and you see a huge, beautiful chandelier, in this case, or some lasers on an optical table. This chandelier is just the fridge, and what I wanted to draw your attention to is the electronics that sat next to it. On the, you can't see that, okay, never mind. In both cases, so the electronics for the AMO system are up at the top there, and what they're doing is generating microwave signals, and this is how we control a quantum computer. What is this compute really doing? This is actually quite a small quantum computer in both cases. We're talking around 100 physical qubits, and you can see you need quite a lot of control electronics even for that, right? And we need to get to hundreds of thousands, if not millions, of physical qubits. So scaling this up is going to be a really interesting problem. Of course, there's going to be some amazing physics and material sciences and refrigeration, but there's also going to be some great classical electronics to build. So what is this classical system actually doing? So most of it is implementing quantum error correction. So there's a nice plot here from a paper in 2017 that shows the total instruction bandwidth in a quantum computer as you scale up the number of qubits. And so it's on a log scale, and we're getting to 10 to the 14, 10 to the 15 operations, and most of what those operations are doing are implementing a quantum error correction. And just to kind of give you a sense of where we're going here, the total number of operations, or the amount of data that's coming out of a quantum computer as we get to millions of physical qubits is on the order of 100 terabytes per second, which is like Netflix global streaming. So if we go back a step, we're going to build a computer that has a fridge, and next to it, a classical computer that's going to be processing the same amount of data as Netflix currently does worldwide. So this is the scale of the challenge. And I think one of the reasons it's really interesting is that it's not just an amount of compute, but it's also the timescales that you have to solve those computational problems. So you can kind of think about what the timescales of the classical compute across the stack. So I've picked out some numbers here. I mean, these are mostly for solid-state systems, but it's really just to give you a sense that across the stack, there are multiple different operations happening to do with conditional operations, changes in the control flow, updates to the parameters, and these the things that we're trying to implement have different timescales associated with them, right? So, for example, solving the decoding problem in quantum error correction needs to happen at a rate of roughly megahertz, whereas you can do your kind of large-scale compilation on the time scale of minutes to hours, right? So there's a bunch of different operations here that all have different timescales. And these timescales put serious constraints on what you need that classical compute to be doing. So I'm going to dive into one of these topics to give you a bit of a flavor of like what exactly is this computer doing, and in particular going to look at quantum error correction. So this is how we're going to scale the number of error-free operations beyond the thousands that are possible today to the millions and ultimately trillions of error-free operations. So let's just take a quick step back and let me introduce something called the surface code. So this has become the dominant way of thinking about quantum error correction. It's a really beautiful example of how we can encode information in quantum systems. So this is a picture of a logical qubit, so one logical qubit. Each of the green dots are the data qubits. So these are carrying the quantum state of the computer. And then the black dots are the ancilla qubits that we add to check if there have been any errors or not. So there are two different colors in this patch. You've got the red colors and the green color. These are checking for the two different types of errors that can occur in a quantum system. So I'm just going to focus on one, which are so-called X errors. These are like bit flip errors. And so what these checks do, so you have one red box, you essentially check, did I measure a bit flip on any of the 4 qubits? Right, so you check the parity of those 4 qubits. And if the parity is odd, then the syndrome, so this black qubit, lights up. So you can see here in this example, there are 2 X errors, and 2 of the syndrome bits have lit up. There's one in the middle that's flipped twice, and that's because it still has even parity. Right? So there were 2 errors. So the decoding problem is, we don't see this picture. What we actually see is this picture. So we see the changes in the syndromes. And then the decoding problem is to, given this information, what was the most likely error? And you can see that there could be different ways to create that same error. In fact, any path from these 2 endpoints would be a valid explanation for these syndromes. And then the shortest path, so the one with the fewest number of errors, is the most likely because errors are occurring at a rate of, say, 1 in 100, 1 in 1,000, so fewer errors is more likely than more errors. Right, so we're looking for solving the shortest path problem in some grid. Okay, so here comes the test. So now I've explained how quantum error correction works. See if you could solve this problem. So here are the endpoints. Anybody can solve this by the end of this talk, I'll buy you a drink. So the actual problem is much bigger, of course, and we see lots of errors, or the syndromes from lots of errors, and the task is to figure out, well, how do I best explain this? So given the data, what's the most likely error? And then I'm actually simplifying things again here, because actually the measurement of the syndromes itself is noisy. So there's nothing perfect in this quantum computer. So in fact, the real decoding problem looks more like this. Right, so there's this huge grid of possible syndromes that are all lighting up at a rate of a million times per second. Right, so we're getting new data a million times per second. And so the decoding problem, or the problem of the classical compute problem for error correction is really it's a high accuracy. Like, we need to be good at solving this inference problem. Otherwise, we're going to make a mistake. It's high throughput, so there's going to be a lot of data coming out of this quantum computer, and it needs to be low latency. What I've drawn here is the clock cycle of the quantum computer. So kind of down at the bottom, you have the qubits. You measure this data, solve the decoding problem, and send a correction. You have to do that between every logical operation on the quantum computer. So this defines, the speed at which you do this defines the logical clock rate of your quantum computer. Great, so this is kind of, I think, a really wonderful classical computing problem that comes from quantum computing. And we've been making a lot of progress in solving this problem over the past 5 to 10 years now. So last year, together with Rigetti, we showed that indeed you could get this clock cycle working. So we embedded the Riverlane decoder inside the control system that was generating the microwave signals for Rigetti to show that this whole cycle worked. So this was a great breakthrough, because we showed we could solve this decoding problem faster than the data generation rate. So we could keep up with the error data. And we could do this very quickly. So we had a latency of around 10 microseconds. And I think the kind of interesting thing here was we learned an awful lot of embedding this decoding problem within the full quantum computing stack. So there's more to do, but there's a huge amount of progress in this space. I think the other nice example from last year was the result from Google. And of course, there was a lot about error correction, because this result showed that you could get logical fidelities below physical fidelities. And so that was a huge achievement. I think one of the interesting things here is the way that the Google team approached this was to make use of extensive software calibration. There are imperfections in the fabrication of the superconducting chip, and Google is very good at software development, adds this software layer on top to account for that, or to correct for that. And so there's a huge amount of calibration that goes into this result. So this is another example where classical compute is used extensively in quantum computing. So all of these, Peter showed this plot. So on the right-hand side, you can see the physical fidelities of multiple different qubit modalities over the past 2 decades. It's a huge progress in the field. And I think one of the interesting things here is a lot of this has been done repurposing stuff from other industries. Most of the control electronics is essentially built by Xilinx to develop 5G base stations. It's not built for quantum computing. And so what excites me about the next decade in quantum computing is the specialization, the building of components that then continue to drive forward quantum computing. So the second point here is, as Andrew pointed out, the roadmaps of multiple companies in this space get us to around 10,000 physical qubits over the next few years. And together with error correction, this means we can build the first error-corrected quantum computer. This will be called the megaquop, so million quantum operations. And I thought it was interesting just to compare the computational power of that computer. So on the on the right-hand side, you can see the megaquop spec. So 1 million error-free operations. That's around 1,000 to 10,000 times more than current quantum computers. And it will have around 100 logical qubits. Now, if you wanted to simulate that quantum computer just very directly, using the best known simulation method, you would need on the order of 1 billion trillion GPUs. So that's just to say it would be impossible to build such a system. So this will be the first quantum computer that nobody can simulate. We saw an interesting example from Andrew about the first application for that. I think we need to, there's a huge potential to come up with new applications and more applications for that. And it's the first step in a much longer journey. So having built the megaquark quantum computer, the next generation will be the gigaquark, and then the teraquark. And as we increase the number of quantum operations that are possible, then the application space will grow enormously. So I think this journey will be one of both science, it will include amazing engineering, and I think the third thing that will enable it is the specialization of key components within the quantum computing stack, people dedicating resources to solving particular parts of the whole problem for quantum computing. Great, thank you.
Our next speaker is Dr. Richard Murray, co-founder of Orca Computing. Dr. Murray's PhD was in quantum atom optics, and he previously worked for the UK government supporting Sir Peter Knight and leading the innovation activities for the Quantum Technologies Programme. Under his leadership, Orca Computing has grown to a team of 65 people and has now established US headquarters. So today he's going to tell us how photonics is different from other quantum computing modalities and why that's a good thing.
Thank you very much. Before anyone freaks out too much, we don't have a US headquarters yet. We have a US presence, not a US headquarters. So thank you. So just to explain, yet. So just to explain the title of my talk, I think it's interesting and incredibly impressive to see all the plots that Steve just put up. I don't think anyone is surprised when you sort of observe that photonics quite often isn't featured on those plots. And so what I decided to do to this type of audience is to really explain why. And because in many ways photonics is really exciting, you know, it's a promising quantum platform, it's very different from the rest. And so what I decided to do slightly dangerously, especially if you remember that my background is in atomic physics, is try and explain why photonics is so different, but in a way that hopefully is somewhat calming. So it's very different. The way we process quantum information is different. But in a way, there's a huge promise, and there's an advantage in doing it the way that we do, in a way that I'll try and explain. So before we start, happy International Year of Quantum. This is actually a Royal Society picture, and I heard that it was not deemed respectful enough for the Royal Society brand to show. But having spent a career not being maybe as respectful as I should be, I thought I'd stick it up there. So congratulations, Royal Society. Happy Year of Quantum. And just to take a moment to... Peter's shaking his head. But just to take a small step back and just to congratulate ourselves and also embarrass other people. About 10 years today, quantum was kicked off in the UK, and it is truly impressive how much vision and leadership the UK showed. So 10 years ago today, several people got in a room, quite close to here, to sort of kick off a lot of quantum activities. And I thought I'd just zoom in to further embarrass people. And what's been really great is to see the progression of the field and to see many of the cast members that we know still around and still progressing. So just to start in a very simple picture, what are the key ingredients to making the perfect qubit? And I actually often describe it as being a quite significant contradiction, because what you really want is perfect isolation. You want, and the reason we have quantum information in the way that we do in the first place, is our ability to isolate atoms, electrons, photons, perfectly excluded from the outside environment. So the first thing that you want to have long coherence times is something fundamental that is not interacting at all with the outside environment. Of course, the contradiction at the same time is you also want to do something with that. So the contradiction is that on top of that, you also need perfect control of that somehow perfectly isolated thing. And I think it's interesting when you look at quantum computing, you see a sort of dichotomy. You see sometimes people present perfect qubits, long coherence times, But at the same time, you also see the desire and sometimes people reporting lots and lots of control, lots and lots of operations. And if you really want to squint, it's hard to see platforms that are truly in the middle, ones where you have true isolation and you also have perfect control. And of course, people are working on this. I show this as a distinct setup to photonics. So photonics, and the reason why quantum networks are the way they are, heavily over on the left-hand side. It is easy for us to have truly isolated platforms. When you have a single photon down an optical fiber, it's very hard, in fact, to see that interacting with the outside environment. That is why photonic systems work at room temperature and all the rest of it. It is natural for photonics not to interact with things, which of course presents our biggest problem. Well, how do you get it to do anything? How do you get single photons to interact with one another, to do anything that anyone needs to perform gate operations and things like this? So I think it's interesting to compare the two, and I don't think it's a bad thing that photonics has this challenge. You start from a great starting point of having a really truly isolated platform that has a lot of advantages. So my co-founder, Josh Nunn, loves to show up pictures of Star Wars. If you really haven't understood what I'm talking about so far, Josh loves to say, the challenge with photonics is Star Wars isn't real. When you have lightsabers, photons don't bounce off each other, they don't interact with each other. So in real life Star Wars, it would be a little bit less sort of sexy. You'd see two guys flashing different coloured light bulbs at each other. And of course, the lightsabers go straight through each other. But as a photonics company, as someone trying to perform computation with photons, we have to enable photons to interact with each other. We must have interactions between photons, and we must have sort of 2-qubit gates. Not my work, and in fact probably the work of many people in this room. The way that's been approached so far is through what's known as measurement-based quantum computing. So this is where you don't have what we're all used to, static qubits, and you perform qubit operations on those qubits. You basically send single photons into a big interferometer, and you rely on the fact that you can measure those photons in particular ways to firstly create entanglement, and then also to measure that entangled state to perform sort of what is gate operations. So in this picture, I think helps explain why photonics is so hard to compare with other platforms. You need to do all of this. You need to generate this massive lattice before you can start talking to anyone about a 2-qubit gate. And that is one of our, especially someone who speaks to investors a lot, one of our hardest problems. The question all investors love to ask, because it matters a lot, what's your 2-qubit gate fidelity? They don't really like the answer that says, well, 2-qubit gates are really hard. We have a great way to scale those 2-qubit gates up once we have them, but why don't you wait before we built up this lattice and done this? So this measurement-based scheme is very attractive. And by the way, I love the sort of fact that what you're really doing is sort of separating the job of isolation from the job of control. You're sort of separating the long qubit lifetimes that you can get with your single photons from the job of interacting and measuring those photons to carry out gate operations. So in some ways, it's quite a clean way to approach it. And indeed, that's why it's quite promising. It's just different, and it's just, in some ways, it takes you to more effort to get to that point of being able to do that. I think one other common feature that people raise with photonics is, you can do all this, but you require a lot of detection. You'll see you're constantly measuring these photons in order to create entanglement and also create operations on those. Again, not a big problem, but it just requires a lot of detectors, which people are scaling up. So at Orca, what we've started to do is to sort of say, okay, other people are gearing up to that way of performing linear optical quantum computing really well. How can we try and beat them to it, quite frankly? How can we introduce new components that sort of change this model from a linear model to something more deterministic, something that looks a little bit more like a gate-based operation? So what you'll see now is Orca's slightly different slant on how to address this problem of approaching photonic quantum computing. The first, which is what many people probably know us for, is that we started life with a quantum memory. So we've always been a company that has photonics interacting with atoms, and what's sort of beneath the surface progressing really well in the company is increasing efficiencies, increasingly low losses when you try and take one photon and capture it within a rubidium ensemble, then turn it back to a photon again. We've gotten really, really good at having these rubidium cells that capture photons, and then we can release them later on. In fact, our memories have become so good that we've started to now prepare for using these same cavity-based atomic systems to perform nonlinearities. So the photonic picture is true, linear optics completely true. How can you change that? Well, you introduce a medium which is not linear. And there are many different ways of doing that. Quantum dots is one. But because Orca has had this tremendous track record of doing atomics and photonics, we've been moving forward very nicely towards implementing nonlinearities using these very, very efficient rubidium cells. And let me just say, if you can do something like that, all of a sudden you move to this very resource-intensive linear scheme. Fantastic, very low noise, and it could be very promising, but quite likely very large, very expensive, to something that's a lot more resource efficient, potentially a lot more compact, maybe a lot cheaper. You eventually reduce the number of photons that you need dramatically. So when we're looking at things, if we can build on this platform and introduce a new component that changes the way you approach photonic quantum computing, that's quite a good thing for us to look at. The second thing we look at doing, which also leverages what photonics is really good at, is accessing frequency. So, it's quite easy to imagine things scaling up, and just build more of them. That's great and promising. But another really exciting thing that you can do with photonics is scale up just by accessing the sort of degrees of freedom that come for free. And anyone who's spent any time in telecoms knows that the reason you get very good internet, very good Netflix on your phone is because of sort of the accessing frequency space. So frequency divisional multiplexing. The transmission of information across many frequency channels is really well known. What hasn't happened so far is copying that same technique with single photons. So again, to be able to produce the same outcome, this large-scale photonic quantum computer, but with significantly less resources, we've been progressing some component technologies that allow you to create and then address a whole sort of plethora of different frequency channels within a photonic system. And you can see here, it's really easy for us to generate many, many frequency channels, each of which that can be considered sort of an individual comparable to an individual sort of channel. So another great way for us to be able to scale up these systems without resorting to just massive size and massive cost. So those are two of the sort of promising things we think we'll be delivering into photonics over the next few years. I guess I thought I'd take a step back and really define what we think is our raison d'etre. In our view, it is critical that quantum computers are delivered as things that look like computers, stable products. Anyone looking to use a computer, quantum or otherwise, cannot survive lots and lots of errors, constant maintenance, PhD students coming and going, calibration every day. Quantum needs to mature rapidly to be a realistic prospect, especially if you're integrating those systems with classical compute. So again, photonics has an advantage. You can build these sort of robust systems based on telecoms, and hopefully many people know already, we've delivered many of these systems into the market, 9 to date, and we're launching our first sort of PT2 delivered to the NQCC later this year. So it might sound sort of boring, and I know several of our competitors tease us for what, black boxes and things. Unfortunately, having had a career largely based in industry, delivering sort of stable, boring products in black boxes matters a lot. So we also, even in quantum computing, we think that matters a lot. And it's a sort of new frontier of challenges alongside the performances that people are continuing to evolve. So what do we do at Orca, just to sort of wrap things up a little bit? I guess we have sort of 4 activities, 4 philosophies, things that we try and do. As I've already explained, firstly, we really do like delivering quantum computers. So we deliver real on-premises quantum computers to different customers. And as I said, we've sort of had 9 of those installations to date, which is a great learning experience and a great success of ours. I love to show investors pictures of people loading things on the back of vans. What's so equally as exciting to boring people like me is the opposite side, unloading the quantum computer, where you hear stories of installations taking years. That's years of people waiting for their machine to come online. We do it in sort of a matter of, I think, half a day is our normal installation time. So we deliver quantum computers, as boring as that sounds, it's very important. As has been picked up in some of the comments earlier, we also thoroughly believe in integration of quantum systems. So it has been made clear how important quantum and classical side-by-side is. I mean, Orca has had, in fact, a leading Innovate UK grant called the Quantum Data Centre of the Future for the last 3 years, where we specifically looked at how you can have a quantum computer side-by-side with a classical one without everyone spending a ton of time learning quantum physics, embedding all of that within a integrated software layer and a hardware layer. So we, again, very, very confidently believe that integration is key and comes down to doing really boring things really well as well, so working with NVIDIA to make our systems run through the existing software stack. Maybe less on the business side, but more critical to the evolution of the industry, and also something that we believe in is education. I mean, it's not the case that everyone knows about a quantum computer today, and quite rapidly people will need to upskill rapidly. And even in the UK, you meet young students who need to know about how to program a quantum computer. You go to different geographies where places like Saudi Arabia are wondering how on earth they could ever use a quantum computer if they don't have enough skilled people. It's been truly amazing for me to be able to support the education of people, young people, old people, people from established companies, through Orca's activities in supporting and running hackathon events and community building activities. For example, like the one we do with the digital catapult, which is now onto its second cohort of industrial users. And then finally, and I guess most controversially, is the application, which no one really knows about, but Orca has a very ambitious target to make near-term quantum computers useful, applicable to industrial problems. Now, there's a ton said about near-term quantum computers and their applications. I think it is fair to say that a lot is not necessarily sort of realistic industrially, but Orca treats this problem very seriously, and we do look at things like machine learning models and think hard and challenge ourselves on where exactly can quantum computers be a useful component. I think it has been something I think is probably fair to say a breakthrough, identifying certain parts of machine learning models. In this case, it's the input layer, so the input sort of vector space that gets fed into generative models, where you can find benefits from accessing quantum statistics, sort of quantum systems as an input layer to those models. So that might sound boring. We're not actually performing many gates when we do that. But what's not boring for our customers is that you can improve generative models if you do that in a way that we don't think can be copied classically. And companies don't care how quantum your thing is, how many gates it's got. They just want to desperately see applications to get them confident that they should continue to invest to get to all the things that we love about the quantum, the error correction regime later on. So in our view, all of this late stage stuff is critical, error correction critical, but as a company building hardware, we really want and believe it's important to find near-term applications so that companies can use those things to progress their interest, to find new applications, so that we all have the money and the funding and the investment that we need to continue our journey towards ever-increasing size quantum computers. So the application for us, especially in the near term, is something that I don't shy away from. I know many people in the audience, quite rightly, are critical of. I don't mind people challenge me on this point, but I will not hide from the fact that I think it is important for the quantum community to find near-term applications of quantum while we get on with the other jobs about building larger-scale quantum computers. So that was sort of a whistle-stop tour through everything we do. Thank you very much for your time.
The final speaker in this session is Dr. Elvira Shushanina, who is the Senior Director of Strategic Initiatives at Quantinuum, where she leads efforts to explore industrial pathways to quantum advantage. Her PhD was in mathematics, and she previously led quantum computing research for material simulation at BMW Group. Today she's going to tell us about the transformative value of integrating quantum technology with AI.
Thank you very much. I perfectly realize this responsibility to be a barrier between you and lunch, so we'll try to be efficient, and very happy to be part of this session on enabling technologies, because I would like to speak about one of my favorite topics, quantum and AI. If classical AI can actually be an enabler for quantum commercial value, and in return, if quantum technology is mature enough to redefine or enhance the classical AI models. But let's start with quantum maturity first. So I came to the industry in 2019. It was literally a few months before the famous Google quantum supremacy announcement. And as probably many of you, I was mind blown by the fact that we could already do tiny simulations with large yet errors, but on already existing quantum computers. And that clearly marked this path from lab to the industry, from the discovery to the engineering phase. But back then, it was still not really clear how will we manage this journey from the tiny simulations towards addressing the humanity's most challenging problems. And it was full of skepticism and, as you know, hype as well. So today, I would like to show you something extraordinary and hopefully to bring a little bit of light on where we stand with quantum technology today. So this image here shows one of the most critical reactions in electrocatalysis, the dissociation of the oxygen on the platinum-cobalt surface. This fundamental yet but incredibly complex process has a direct implication on the performance of hydrogen fuel cells that are used in aviation and automotive sector and that are crucial components for future sustainable mobility and energy transition. As you know, nowadays production of hydrogen fuel cells requires a lot of very expensive metals such as platinum, and because classically the mechanism of this reaction is still fundamentally uncovered, classical solutions struggle to study it because of complex magnetic effects and strong electronic relations. We don't really know what would be the better substitute for platinum to produce better, cheaper, and safer fuel cells. So together with our partners from BMW Group and Airbus, we pioneered this research since 2021, and we were able to get to some very exciting results. So this was the first quantum study applied to a realistic use case of heterogeneous catalysis, where we were able to not only accurately describe strong static and dynamic relations, but also for the first time approach the combined effects of magnetism and surface relaxation that was never done before. And we were very happy that those results were acknowledged by Nature and published a few months ago, practically setting a new benchmark in the industry. But being motivated by the real-life applications, it's not only mean development as state-of-the-art software solutions, of course. As a full-stack company, we've made this long journey to solve some very critical engineering challenges and progress on the hardware side. So since practically our foundation, whether it was the demonstration of the first real-time error correction or achieving the world's most reliable logical qubit and then executing the end-to-end chemistry simulations on 12 of them. And then earlier, a few months ago, we also were managed to entangle 50 logical qubits. This not only shows our commitment to the fault tolerance, but also our confidence to actually deliver the fully universal fault-tolerant quantum computer with hundreds of logical qubits already by the end of this decade. And 100 of logical qubits here is not just a large number. When it's powered by the advanced middleware and software, it can actually place us at the edge of practical quantum advantage and commercial value for a broad range of application areas, including quantum and AI. And here probably this would be a very good transition to the second question about how powerful this synergy between quantum technology and AI could be. So for most of you, probably it's not a secret that classical AI can actually be used to build better, design better computers, optimize the circuits, and also improve the error correction, and it was discussed partially already here with our speakers. And as a proof of that, our recent collaboration with Google's DeepMind, where we tried to use the reinforcement learning techniques in order to reduce the amount of very expensive and tricky TOEFL gates in the circuits that basically are the main responsible for the practicality of quantum simulations. This collaboration was pretty successful. Our alpha tensor method was able to reduce the computational cost of the circuits for different applications from 37 to 47%. But probably one of the most fun results, I would say, is that this classical AI model was able to identify some very complex patterns and actually rediscover some of the already known optimization techniques that originally took researchers years to be established. And that shows how actually powerful classical AI can be in order to optimize this process of discovery of new optimization techniques and tricks and accelerate the development of a quantum technology. But despite being very powerful, classical AI and specifically generative AI has its fundamental limitations, specifically when it comes to the interpretability of complex physics phenomena. And in this case, quantum actually can be very much helpful by providing access to the previously inaccessible data, or we call it quantum data, that can only be computed on a quantum computer. Either it's ground state energies of molecular systems or some sophisticated encryption parameters. Providing access to this quantum data and uses this quantum data to augment classical database and then to run classical AI models can actually provide the improvement of model accuracy and also increase the speed to solution. And I'm not speaking about the potential advantage of energy efficiency, which nowadays I think becomes very critical when you literally hear that people use entire nuclear plants to power the most advanced classical AI models. So for 2025, our focus is actually bring it to life. And as a targeted application, we decided to tackle the problem of targeted drug delivery with the specific particles called metal organic frameworks. Just for your curiosity, metal organic frameworks are the particles with a large amount of or large volume of pore surrounded by the transition metals. And those transition metals can actually attract the medication, and then being injected into the patient's body, they can travel straightforwardly to the tumor or other sickness areas, and then safely release the medication under the physical chemical conditions set externally without damaging the rest of the healthy body of the patient. Fun fact, but actually we accumulated over 4 years of the expertise working on those types of particles, but for completely different application. Those same metal organic frameworks actually can be used for capturing carbon from the air, and this is what we did together with our partners from Total Energies. So to summarize this up, we hope that by bringing together the most advanced quantum hardware, plus the power of generative quantum AI, and our expertise accumulated over 4 years in studying quantumly those particles, we will be able actually to bridge this pathway towards meaningful products that will be able to redefine the future of precision medicine. And this is just one example how quantum can affect one of the fields such as biomedicine. But we also plan to expand, or we're already doing today, expanding this idea onto some other very important critical areas for real life. Together with our strategic partners, we build the important IP today in order to improve the geophysical resource exploration or develop new sustainable energy solutions, solve the problem of food security, climate change, and even secure the digital infrastructure. So we do believe that by bridging this gap between the best of all the technologies such as quantum, AI, HPC, and enhancing it by the subject matter expertise that comes from our partners, we will be able to secure the important foundations and reshape the future of innovation today. Thank you very much.
Three excellent talks, and I'd like to invite those speakers up onto the stage for the question and answer session. We have plenty of time, so just a reminder to those watching online that you're able to submit questions via Slido, and a reminder to those in the room, please await the microphone before you ask your questions so that those online can hear. Okay, the panel's open to questions.
Thank you. This is mostly addressed to Richard, but you might all have views on this. It's a general question that crops up when we're talking about the different platforms that exist for quantum computing. And Richard, you were particularly keen to stress how important usability was, easy usability of these devices. So that's a matter of getting the right software as well. And my impression is that at the moment, the software is platform dependent. And I wonder how much that is an issue, particularly in terms of whether there's enough work being done on developing software for all the different platforms that exist, but also is that going to remain a problem for users, that they're going to have to learn a particular sort of software for the platform they've gone for?
Yeah, I think it's a really good question, and I think probably my panel members can say something on this as well. I think, I mean, I'm not a user, but I can imagine from the perspective of users, what I've heard is that you really don't want to train all of your workforce up or be a user and train up to just use one platform to then find that that knowledge doesn't apply to any other platform. And you're right in saying I think that's probably the case at the moment, especially because a lot of the platforms require you to come right down into the quantum physics of things, which is a necessity because we've got everyone's trying to maximize performance that they've got, which requires access at the low level sort of layers. I think it's probably a maturity question. I think probably, in my view, the companies will start providing platforms that allow abstraction, and Rivelane's done lots of work on abstraction layers and things like this, because no user wants to really, if they're doing their job, talk about quantum physics when they're trying to do machine learning or something. It's a hobby. It's not what their job should be. So I think it's the job of, I don't know if people agree with that. Real people who have day jobs might spend some time looking at what quantum superposition is, but it's not, that's time spent away from them programming things to provide value to their company. It's a big distraction, big investment the company has to make for no good reason. Long story short, I think it will be the case that the platforms will become such that the companies will do more to make the user sort of feel at ease with whatever they're doing, hide the details underneath. But I think that probably does require better understanding of the use cases, better understanding of the users, and probably better hardware as well that you can afford. Let's be honest, whenever you abstract things, you lose performance. It's less efficient. So when you're abstracting up from the lower layers, you need to have the performance to sacrifice to perform that abstraction. But I'm speaking on behalf of... the other two panelists have done also work on this, so I'm sure they'll have a view.
Maybe I could just build on your point, Richard. So I think there's an important distinction between NISQ and error-corrected quantum computers. So an error-corrected quantum computer at the physical layer is doing exactly one thing. It's doing syndrome extraction, nothing else. So there's no other operations that are happening at the right down at the qubits. And so there is this really natural layer in which software development happens on an error-corrected quantum computer. And so I think a lot of the reason why it feels very janky right now is because pre-error correction, people are compiling all the way down to the physical operations. They're looking at specific gate rotations and so on. So I think that's kind of, I agree with Richard that it's a statement of the maturity of the technology today. The second thing I would say is that actually there's a massive opportunity right now to become a software developer in quantum computing, and I think this is really exciting. Now you can program the first error-corrected quantum computers. They'll have one logical qubit or two logical qubits, and you might think, oh, that's really boring because all I'm going to do is two logical operations. Actually, how you do that logic is a super interesting question. There are loads of different ways to implement logic, different codes. This is a rich space in which many people in the research community and in companies are exploring right now. So there's a massive opportunity to upskill in developing the software skills and the skills for programming the first error-corrected quantum computers. And maybe just to put a figure on it, I think there are probably 500 people in the world who have this kind of skill. It's probably not more than that, just judging by kind of number of people who go to error correction conferences. So a national program, say in the UK, could train realistically 500 people in 5 years. Why not? That would double the number of people with that skill, and half of them would be in the UK. So I think that would be a huge opportunity for the UK.
Maybe just a quick comment on my end. It's very important to make quantum user-friendly because more people could be involved, and broader we have the range of expertise, faster we could be able to develop something tangible. And as I shown on my presentation, we have this full stack image, right? And there are many companies right now that develop a lot of solutions for middleware, operational systems, plus the compilers that basically allows users to get access to a broad range of the quantum backends or quantum hardware and try to get the value for their specific problems for each advantage, from the advantage of each architecture. So this is an ongoing effort, and I can just congratulate people who do this. Yeah.
Thank you. Do we have any more questions?
Hi. So this is a question mainly for Steve, but other people might want to chip in. You had that slide which has which tells us how amazingly hard it would be to emulate 100 really good qubits, a trillion processors, I think you said. But of course, it would be dangerous to imagine that therefore 100 qubits is as good as having a trillion processors, because that's just the job of emulating it. There are many things in the world that it's very hard to emulate that we don't really care about. So my question is, do we have ideas for what we would do with those 100 qubits that might be coming this decade or pretty soon afterwards?
Yeah, so absolutely right. It's a one-way implication. So the quantum computer can't simulate the billion, trillion GPUs, absolutely. So, I mean, Andrew talked about one of them this morning, simulating the Hubbard model. I think there are some interesting ideas. There certainly aren't enough. And I think this is another area where now is really the time to be thinking about it. It's hard to do, of course, because you don't have the computer to try out your ideas. So it's a bit like trying to understand what makes a good quantum algorithm. And that's a problem people have been challenged by since the beginning, right? I mean, it's a really difficult problem to come up with new quantum algorithms. I think we've learned a lot over the last 5 years of reducing the complexity of the approaches that we have already. So kind of what works. I think we know things like symmetry in the system you're trying to solve is going to be good because that's going to map really well. There are a few people in this room who know more than me, but including yourself, Simon. But so yeah, I think it's a great topic.
I can also add slightly tangentially. I mean, it's a silly point, but there is a huge value in just providing the tools and letting people get on with the job of finding out how to use those tools. And at least in our experience, we've sort of launched this thing, which is not really a universal quantum computer. It's still a quantum thing, and it's still interesting. We've been amazed about the number of different users that have taken that and run with it, different research groups that have found applications. And I think, to take Steve answering it slightly different, it's sort of amazing the capabilities of a machine like that and what it will bring and how much creativity and applications it will unlock. I don't know if other people would disagree. It doesn't worry me that much that we can't pinpoint exactly what a system like that will do, because it's probably without doubt that people will definitely be poring over themselves to use that system and find applications. So it's just a bit of a timing thing, in my view as well.
I think we have another question at the front.
Great, thank you. Really impressive to see delivery of hardware. I've got a question about the interface between electronic classical computing and the photonic platform that you described. So predominantly classical computing is electronics, and you're talking about photonics. So how complex is that interface? And do you envisage a growth in the photonic platform, more and more computing capability being moved into the photonic domain as time progresses?
Ooh, this is a tough question. I think the simplest answer is it's not too hard at the moment. I mean, there are, of course, many different layers to this question. Fundamental layer, we're running electronics really, really fast, but that's not what's being handed over to the classical computer. I think what's missing at the moment is a lot of just integration with existing classical HPC workflow models. You know, like existing software tools that everyone is currently using, and just the fact that quantum needs to integrate with that. I don't think it's hard. It just has to be thought through and done. I think that as the size of any quantum system scales, the integration problems scales. And this is probably now a Steve point, but it scales even harder. And you know, there are all sorts of different sort of questions about, you know, if you have sort of non-localized quantum information, you have loads of systems, loads of quantum computers under one system. What do you do with all of that? How do you orchestrate all of that? So it's a not very good answer, but I think it's not too hard now, but it just needs doing and doing well. Doing well is important because these things can't fall over. I mean, we're sort of excited but also terrified about doing this in real data centers where there is zero scope for the thing not working. Like, you get phone calls and get shouted at if your system stops working, or at least you should. So the thought of doing all this well enough so that quantum stands up to that type of scrutiny is really hard, but not hard in itself. And then it scales even, the challenge only becomes more challenging.
Just a question for Richard. So your little memory cell, nice little memory cell. I was particularly impressed by the soldering.
Funny, I was desperate to find, and this is the thing about technical teams, none of them take photos of anything. I was like, give me a photo. Anyway, fine, yeah.
Can you say how many of those you need in that thing you were taking off the back of the truck? And if it's a lot, or if it looks like it's going to be a lot, how would you scale that technology?
Good question. It does need to be. I mean, you need one memory cell per photon, per qubit, and you need lots and lots of photons. So we are looking ahead at, well, this is a question about priorities. The team have spent a long time thinking about scaling it up, and you can have arrays of things, like many, cavity arrays inside of vapor. The key, it's a bit of a mistake to do that too early, because the key challenge is still efficiency. It's still the fact that we're at, I think, 85-90% efficiency, and we need to get to 95 to 98% efficiency. So it's a sort of the scaling thing doesn't worry me. You can have clever schemes like hollow core fiber, or sort of using fibers for sort of lenses and things that allow that thing to scale. What we don't have at the moment is the demonstration of how the quality that we need to do that well, if that makes sense. But I mean, this is actually now a point about not us doing this alone. We're now interfacing with a community of AMO people, cavity people who can do this well. And so when I say we, I don't mean we, I mean that we find suppliers to do all this stuff. But there are many out there.
So my question's about dynamically reconfigurable systems. Sounds a bit weird, doesn't it? So I've been involved in AI research the last 30 years in developing, using semantic AI to deliver dynamically reconfigurable systems. Could one envisage exploring dynamically reconfigurable hybrid quantum classical solutions where how they are composed together in a solution and system changes incredibly dynamically? I mean, not now, but can one even envisage contemplating these dynamically reconfigurable hybrid quantum classical solutions? And if so, exploit semantic AI. There's 30 years worth of research in the area.
Can I take this one? Hey, photonics. Well, yeah, I don't know. I'll give you a point later, Roberto. Let me take a step back and talk about sort of networking of quantum systems, which many people talk about. I mean, there are lots of really impressive demonstrations of an optical link between two different types of qubits. It's very undynamic at the moment. It's very unconfigurable at the moment. So I guess if I'm sometimes allowed to elaborate on the future of any photonics platform, I always describe this world where one day you'll have a number of different nodes, maybe they're photonic, maybe they're ion, superconducting, whatever. But in the middle of that, you'll have something that essentially looks like a large-scale photonic quantum computer, i.e. all the things that we build, a very, very low loss, highly reconfigurable fabric, interconnecting qubits, photonic or otherwise. So that is the world which will deliver all-to-all connectivity across the whole system at a low loss. And I think it's exciting for a photonics provider how we might do our own thing, but also one day fit in, but not in a simple way, in a way that really challenges the platforms that we're building today for our own purpose, photonic quantum computing. So I don't know if this is answering your question, and everything we do is build reconfigurable networks, systems for computing. So it's sort of what you've asked is actually everything that a photonic platform needs to do to work. All of the measurement-based quantum computing is a big reconfigurable network. So we are doing that. And one day I believe that will become critical in any platform as well as just the photonic platform. I guess. But that's my answer at the hardware level. I don't know if someone wants to answer at the software level and others.
But it's also exciting for our providers. Like for us, integrated photonics is basically the way to scale in order to get to this holy grail of universal quantum computers, fully fault-tolerant quantum computers. And basically this solution that photonic can create this distributed quantum computer while merging with ions or some other architectures. This is, well, it was known, but it's still a hard engineering challenge, so we hope to get there. But yeah, fully agree with you.
As reluctant as I am to put a stop to the discussion, I know other people have got questions to ask, but we've now run out of time, so please find the speakers over lunch, which will happen now. So let's thank all the speakers. Fantastic, thanks very much. And we'll pause for lunch now, and the next session will start at 1:45. Great job.
Okay, can we sit down? Start the session. Let's give a few seconds for people to sit down. Okay, welcome back. I'm Lee Lapworth and I lead quantum computing at Rolls-Royce. And we've got a session now on how quantum technologies can scale. I was just going to give one reflection on this morning. So I'm a supercomputing guy. I've been doing it for years and years and years. So it's always good to see that interaction between quantum computing and classical computing, which is absolutely essential. And one of the things I do is I often use GPUs as a lesson that we can learn. And I'll just give you one example from something that we did many years ago with a collaborator. So GPUs came out, first GPU was 1999. So this is sort of early 2000s. We got a code, we put it on the GPU, fantastic. It ran 40 times faster, 70 times faster on the GPU. We then said, let's make it a little bit bigger and run something that's a little bit more serious. So the GPU started talking to the CPU. And that 70 factor dropped to about 20%. And at that time, the two were connected by a piece of string, so communication was the problem. But supercomputing for the past decade has been dominated by communication. So communicating between a GPU, a CPU, and particularly in a supercomputer is really, really important. And that is by way of introduction to our first speaker, who's going to talk exactly about that. So we've got a nice session on this, covering quite a bit of ground. Carmen's going to tell us about entanglement fabrics and communications. Max is going to talk about the other aspect of scaling, which is production. How do we scale up production? And he's going to talk about AGICs, high-volume semiconductors. And then the other aspect of all of this is, are we sure that we've made what we intended to make? And Alexander is going to tell us about metrology and in characterizing and building systems. So a really nice flow and a nice session, and I'm really pleased to be chairing it. So let me start with Carmen. Where's my list? So Carmen Plaquios Berraquera. So she's a founder and chief executive of New Quantum, and prior to New Quantum, she earned a PhD in physics at the University of Cambridge. Now, I'm only going to give short introductions because I think you'd rather hear from Carmen speaking than me introducing her. So, Carmen, please.
Thank you. Thanks so much. This is a really, really nice event, so thanks for having me. Yes, so I'm going to talk about scaling quantum computers, specifically via a distributed modular approach. So what we build at New Quantum is the networking infrastructure that will allow us to create entanglement links between intermediate-sized QPUs or quantum processing units so that we can create one large distributed computer that can reach the scales that can solve problems that we're all interested in. So this is usually in classical computers called scale out, and this is what has been enabled in GPUs and CPUs before and what we're aiming to enable for QPUs. Briefly about New Quantum, so we spun out of the Cavendish lab, out of Mete Atatürk's group. We're now about 60 people, based mostly in Cambridge, but also a small office in Harwell and in California. We have great partners like Cisco, like the NQC and CERN, and a great multidisciplinary, diverse team. So we're focused on scaling quantum computers. I don't really need to convince this audience about how transformational quantum computers at scale will be, but I do like to say in a slightly simplified way, but I think it's a little bit useful, that 2024 was important because two things were demonstrated out of kind of three that you need to build a large quantum computer. So we demonstrated that we can build really, really good physical qubits, and the record now is Oxford Ionics, so qubits with maybe 4 nines or more fidelity. We've demonstrated that we can error correct them to turn that fidelity into 6, 7, 8 nines of fidelity in the future, and that was the Willow announcement, but also other companies. So we now have demonstrated for the first time that we have stable error corrected qubits, but we have very few of them. And there's a challenge left that is scaling that, and that's a many orders of magnitude challenge. So here we've plotted the qubit numbers, the public roadmap of different companies. And what we can see is that we're approaching some sort of scaling chasm where we're still orders of magnitude below where we need to be to unlock some of the really exciting applications. And the truth is that where that scaling chasm is, we don't really know. We don't really know how many qubits per QPU we'll be able to fit whilst maintaining performance. It's a bit of an unknown. It's a kind of R&D question. But it kind of becomes a question of risk. At some point, the technical risk becomes really high to be able to fit more and more good qubits into a QPU, and then maybe some other scaling strategies need to come in. And of course, what we're really interested in is enabling a modular networked approach. And that's sometimes in quantum we're a bit kind of contrarian to each other. So it's led to a bit of a debate around, are we going to reach this commercial quantum computing regime in a monolithic or a distributed way? It's become a kind of monolithic versus distributed. And I just want to remind everyone that every single large computing system out there, so HPC, AI data center, cloud data centers, benefit from both strategies, monolithic and distributed. So scale up and scale out. Every single one of these systems benefit from advances in having better GPUs and also better ways to interconnect them. And the reason is that for large computing systems, modularity is our friend. We can always build a larger computer in a modular way by knitting together our best processors than by trying to make that processor be much faster, much more powerful. It gives us a way of building large systems with higher predictability and lower risk because we're putting together things that we've already built. Again, modularity is our friend. These systems, if we have modularity, we can swap out components that don't work, and that makes the system more reliable and more robust. And that for quantum is very interesting because I'm sure everyone here knows that quantum processes have a calibration time. So every once in a while, you need to stop the circuit that you're running to calibrate. And that's another limit in terms of the circuit depth that you can run. But you can imagine that maybe a modular system, you might be able to run those calibration cycles sequentially so that the whole system continues to operate and continues to run whilst you're still carrying out the necessary calibration. So all in all, I think a large-scale quantum computing system really benefits from modularity and from a distributed approach. So what do we mean by a distributed quantum computer? So if we have, on the one hand, a monolithic, just a quantum processing unit with qubits inside, these qubits are entangled together in some way, what we call a connectivity. Then a distributed quantum computer is simply many of these QPUs put together and linked with entanglement links now between qubits that are in different QPUs. These entanglement links is the same entanglement that exists inside the QPUs, but just between QPUs. And the role of the network is purely to create those links. That's everything that the network does. How do we do that? So I'm going to go bottom up. We start with the QPUs, and we have a device that we call a qubit photon interface. This is the equivalent of a network interface card in classical. What happens here is that at two sites, you create a qubit photon entanglement, and then you capture those photons that are entangled with the qubits that emitted them into fiber. They travel, and they arrive to a quantum networking unit, which is the equivalent of a router. There, what happens? They arrive via a switch, which has previously selected which two QPUs you want to entangle together to a Bell state measurement station, and then if that operation is successful. If that Bell state measurement is successful, then something called entanglement swapping happens. And so entanglement is created between the two original qubits that emitted the photons. And that's it. That's the link that we're looking for. And that link has just two metrics, rate and fidelity. And creating high rate, high fidelity links between two distinct qubits is our our purpose as a company. We can categorize qubits into two types. So we will build networks that look a little bit different between two kinds of qubits. So there's the qubits that already emit optical photons and the qubits that don't, that interact more with microwave photons. So that NIC, that network interface card or qubit photon interface, differs between those two kinds of qubits. For the first type, it's a little bit easier. It's still really, really complicated, but there you already have photons coming out of the qubits. What you need is an optical resonator or a cavity to capture them with high efficiency. For the other type, so superconducting and silicon spin qubits, you first need to do transduction or microwave to optical frequency conversion, and then use those photons for networking. So we focus first on those types of qubits that emit optical photons, and that's what we're building for. So our qubit photon interface is based on optical microcavities. These are optical resonators that we can place around the qubits, and this is really useful because we can create very high fidelity, high rate entanglement between a qubit and a photon, and then we can collect that photon with really high efficiency. But it also allows us to extract photons that are near telecom and that are time bit encoded. So we've been developing these microcavities for many years, 5, 6 years now, and I'm proud to say that we've now got the best microcavity technology in the world, and we've reached a really, really stringent performance requirements to couple these cavities to single ions and single atoms. We've now put this microcavity technology into two sort of device implementations. One, a prototype to be interfaced with neutral atoms, and we tested that preliminary prototype optically with inflection, and one for trapped ions, which we're testing at the moment in collaboration with the NQCC. So this is really exciting because this is about kind of productizing and engineering this part of the network, which unlocks performance. Once you've got photons, which is really sort of the difficult part, once you've got those photons, then you get into the quantum networking unit or the router, this the switching layer, and the control and orchestration. We've now made a kind of first prototype of this quantum networking unit, which is working in our lab. This is a render, but the real thing exists in the lab, and has off-the-shelf optical components and our own control and orchestration technology. The sort of time synchronization of these systems is really important, so we've set up a collaboration with CERN to integrate their White Rabbit technology in there. Our second generation quantum networking unit will have photonic integrated switching, because that's what we need to enable large-scale networks. We need much lower loss, much higher rate in terms of photonic switching than what we can get actually off the shelf. So with these innovations and with this engineering, this multidisciplinary engineering, what we're aiming is to get beyond the academic state of the art. So there's been trailblazing ion networking groups like David Lucas's group, like Chris Monroe's group, that have really kind of pushed the field forward. And what we're trying to do is to create an engineering company that can take that performance to enable commercial distributed quantum computing systems. Our roadmap at a glance, or the roadmap for scale-out looks a bit like this. We now have these interface and router subsystems. We've proved them. The next stage is to form an MVP of a small network. Whilst we integrate our interface with commercial QPU companies out there, and we're setting up those collaborations with more than one QPU company at the moment, that will enable us to create sort of first distributed NISC distributed quantum computing systems that have our network and commercial QPUs. And beyond that is about enabling fault-tolerant distributed quantum computing. And this is really, really exciting because we've recently put out some results about this. So I had a diagram before about a distributed quantum computer with non-local entanglement links that just went in the nearest neighbors. But actually with a network, what we create is we can create distant entanglement links that have a flexible topology and that are dynamically reconfigurable, someone's favorite words from the discussion earlier. And what that means is that we can enable the use of quantum error correction codes that are more efficient than the surface code, but that require this degree of non-local connectivity. And so in a recent paper, we've demonstrated that building a large distributed quantum computing system in a fault-tolerant way is possible, is feasible, because the requirements on the network are not too hard that we think we can't get there, and it's efficient. So because these codes are much more efficient than the surface code, actually, intuitively, you might think that in order to include networking links, you sort of lose some qubits, you lose efficiency, but actually because you gain so much by the use of these high-rate codes, because you have non-local connectivity, actually the distributed quantum computing system is as efficient, and perhaps more, than the equivalent monolithic system that uses the surface code. So I think this is an important result for everyone. I mean, if we don't need to scale to millions of qubits in a single QPU, but we know that we can connect intermediate-sized QPUs, and that system is, we can build it, and it's efficient, then that really creates a kind of more feasible path to scaling quantum computers. And so what we're really trying to get to is, and what we've proposed in this paper is a modular approach. So how to build a large-scale fault-tolerant quantum computing system that is made of units that have QPU and a stack of networking, and where you build a larger system by adding more of those units, but those units don't change, i.e. that system is truly modular. And that system would then have logical qubits spread throughout, and would be able to carry out efficient logical operations thanks to this network reconfigurability. So this is our approach to scaling quantum computing. Networking can be used to scale other kinds of systems, and I think we might hear a little bit more from other speakers in the session. And with that, I'll thank everyone.
Thank you, Carmen. And I forgot to tell you the thing that you've probably already, but by now, the questions at the end, and if you're online, please post Slido questions. So we'll move on to the next speaker. Maxish, I think I didn't check my pronunciation, I hope that's okay. So again, short introduction, so Max, you can hear Max rather than me. So Max is co-founder and CEO of AGIC, and is a serial entrepreneur in deep tech. I can't even say it. So Max.
Thank you very much, and it's a great pleasure and honor to be here. And I think as many of the people today have had a bit of a memory and reflection when they walked in the building on the start of the very, very early days of the National Quantum Technology Program, and actually the whole activity. It just reminded me that 10 years ago, actually a little bit more, on the very first Quantum Tech Showcase, we brought a toy model of the Hongu Mandel interferometer. And it was literally a toy made with big buttons and LED strips. So it was our fantasy, it was our goal to make it real. And it struck me that actually today I'm going to talk to you about how we do these things at scale in semiconductors, and how that helps us advance us closer to that holy grail of utility scale quantum. And so I've been asked to take that angle on how exactly, what is that secret sauce to bring to life the scalability. And for us, it's, as you can see, semiconductors and something called Foundry. So I'll stop on that a little bit more. But we've started a company on the premise to use photonics to build those foundational products and things that enable us creation, securing, and processing quantum information. Or, well, speaking of modularity, that's your modules that you need for a good quantum computer or quantum network as well. And we started our journey a long time ago, actually. So we started decades ago by the investment that went into the University of Sheffield National Epitaxy Facility, and many, many years and hard work that went into this. So we spun out of this a couple of years ago, and insofar we've been working quite a bit with the UK ecosystem to build up this capability and with some of the key stakeholders that are in this room. And it seems we are talking a lot of photonics after lunch. So I shall remind you again that photons are the most robust qubits. And the reason for that is simple, right? They got intrinsic stability. They exist if you don't disturb them for eternity. That's what they are. They operate at any temperature. They can operate on the sun when it's pretty hot. They can operate in nearly absolute zero or absolute zero if you have it. And it's got a very important feature there is that we actually use photons as our main information carrier in the world. So all of the internet traffic, 99.9% of that is made by photons. And that tells us something about that scale that you can reach with photonics. So for us, the key ingredients to make the utility, they consist of 5 core pillars there. And first one is hybrid integration. And by that we mean that there is no singular material that's perfect for every function. And I think Richard touched on that earlier, with the memories and with other things. And our view on that, take the best of every semiconductor you can find in order to achieve your best performance. Now, foundry manufacturing is a term used a lot in semiconductor industry, but actually it was pioneered by the steel industry, and we're based, by the way, in Sheffield, which is the steel city. So we're back to the roots. But that means very high volume, high quality manufacturing, which is just a standard process that goes. And that's what we want to achieve for quantum to become a reality. And that's critical. Then connectivity. So Carmen just said about, well, let's build connected QPUs, let's build them modular. Now, we need to have a way to connect things on chip, off chip, wherever it goes, and it needs to be the most efficient way to do this, and the most common actually is good. Now, we haven't touched this today on the speed of compute. So it's good to have a fast single qubit gate or 2 qubit gate. How about the speed of 100 or 1,000,000 qubits? How that's going to scale? Is it going to keep up with, is it going to be linear or is it going to go down? And depending on the modality, that's changing, but I think that's an important context. And then robustness. So photons are obviously robust. They're great, but the whole system needs to be robust as well to sit in a data center or somewhere else. So maybe, it can be somewhere in a mobile unit, can be at your home, or who knows. So all of those concepts go into 3 things for us. It's efficiency, compatibility, and scalability. And its efficient operation is compatible with what we currently have in production, in infrastructure, and you can make it big. And I'm going to walk you a little bit through the journey of a photonic qubit. And it's a journey because that's the only type of qubit that's not static. So it always goes somewhere. And in that sense, it's similar to how our normal computers operate because there is a place where you create those qubits, you have to route them, you have to do the computation, after all, you read out. So this is a very simplified journey. So if we were talking about error correction and more complex architectures, this it's going to contain these elements as a key building blocks, but not necessarily in this view. But let's go through all of them. And one of the biggest problems is in photonics is how do you create those qubits efficiently? And our approach to this is to use something called quantum dots in 3-5 semiconductors. So it's compound semiconductors like gallium arsenide or indium phosphide. And effectively operates in a linear mode as an artificial atom which you excite and it emits light. And the great benefit of it, we can drive it at incredibly high speeds. We're talking gigahertz type repetition rate or true clock rate. We can achieve something which is called determinism. That is, every single time we want to create 1 qubit, we create 1 qubit, if that's a photon. Now, moreover, a little challenge there was creating qubits. Are they all the same? And they have to be the same. So you can do this already with this semiconductor technology. And on top of that, it needs to be just one. So you don't have to mess up with the noise. And that's the thing that we've already achieved with this type of technology. And I'm just going to show you, kind of chip to on-chip to package chip to the full complete solution that's running in a standalone mode. And it actually complies with all those key metrics that I've just started. So it's efficient. We're talking up to 1 gigahertz true clock rate. The theoretical efficiency limit is way above 90%. And we're getting to that limit fairly soon, I hope. Compatibility. It does operate at telecom wavelengths. That means we can reuse all of the existing infrastructure. We can leverage all of the supply chain, and I would like to start using supply chain more, word supply chain more, because this is critical to scaling, because somebody's got to make these things. They have to be really high quality. And this is exactly what we can do with indium phosphide, for example, manufacturing. And there is a great amount of infrastructure in the UK already for this, and UK is one of the global leaders in this, in fact. And in terms of scalability, once you go into the foundry production, you can talk about volume. And volume is critical for quality control, for yield control, and all those things that we take for granted from all our microelectronics is not possible without that. And on top of that, it's good because it doesn't require extreme cryogenics, doesn't require extreme vacuum or big lasers. So it's all, I wouldn't say completely commodity stuff, but nevertheless, it does scale very nicely if you make more of those things. So how about routing and computing? Now, these two are sort of similar technologies, but nevertheless, by the way, these are these things here. If I can, yeah, there we go. Maybe not. So these little arm things with arms, those are those Hongo-Mandel interferometers, which we actually brought the other day to here. And Universal Computing Gate is just another implementation of that thing. So again, here we took the route of how do we leverage the existing manufacturing capability, and this one is hugely driven by the existing telecoms industry. In fact, I mentioned photons as being the main information carrier in the world is because there is semiconductor manufacturing to back it up. So all optical transceivers, everything that we enjoy today and this live stream is because there is semiconductor manufacturing for this. Efficiency and the speed here can be much larger. And for a quantum domain, we get up to, say, 10 gigahertz native active switching clock rates. It natively operates at telecom C-band. It was made for this. And state-of-the-art transceivers actually use this technology for highly energy efficient AI data centers and AI interconnects, and also to drive down the cost of your broadband. So it's a truly mass type supply chain. And there is a high volume manufacturing being rolled out, and there is a massive shift from actually microelectronics as well towards more photonics. Even in the big foundries like TSMC are looking into this transition. Of course, it does operate at room temperature, so it's just your normal chip that you put in your pocket in your device. So it does not require any big special requirements to operate it, and that makes it simply scalable because you just add more and you don't require excessive overhead for controls. And so putting that all together, I would like to show you our first quantum computer demonstrator called Artemis, which we are also delivering to the National Quantum Computing Center in a very short time. And in terms of its efficiency, again, we're talking pretty small numbers here, but it's small power consumption, small footprint, small number of qubits for now, but as a technology demonstrator, for us, it's very favorable. And it's compatible with whatever deployment you may choose, including the standard rack space in a data center, or you might put it in a lab, or you might take it on a ride somewhere in the back of your truck. There is no complex controls in this. So everything is nicely scalable and fits into exactly supply chain that we have with normal microelectronics and other industries. So that brings me to mention that you might have noticed that on these things, I didn't talk about the yellow and the green. So the interconnects, which are currently fibers, and the green, which are detectors. And this is something that we put in our roadmap now. And currently we have the Artemis demonstrator, which I mentioned, and you can run some basic demos in terms of boson sampling, probabilistic gates. It's very low swap. It's got all the key components to scale. And something that we're working now on is to bring that all on a single chip with a fully hybrid integrated modularity, and it's a primitive networked photonic integrated circuit that is the central technology for enabling better measurement-based quantum computing, for enabling better networking, and is fully compatible and compliant with those core principles that we're having. And so this is the fundamental stepping stone in order to enable really large-scale quantum. That's what we're looking for. And our take on this is that we're going from the bottom up. So we literally engineer it from semiconductor layer by layer, atom by atom, but we're making sure there is good and reliable supply chain here and a value chain that we can leverage. And it's not just made for quantum, it's made for the whole humanity. And on that note, I would just like to say that let's move the humanity beyond the limits that we currently have. And thank you for your attention.
Okay, so our last speaker in the session is Alexander Salanchuk. Professor Alexander Salanchuk is a fellow at the UK National Physical Laboratory, and he also holds a chair in physics at the University of London's Royal Holloway College. Alexander.
Thank you very much. Right, thank you for the introduction. So this is the title of my talk, and I'm going to cover quite a lot in it. So you let's see how it goes. So first, I will speak about how different quantum technologies may scale. Then something about superconducting quantum computers. I don't think we spoke enough about those. And then comment on the role of metrology and NMIs in this process. Okay, so it's not all about quantum computers, Peter. Sensors, we can definitely make many, and semiconductor fab is very helpful here. We can reproduce faithfully one device after another. So this is another example of the same. It's a microfabricated ion trap, NPL, James Watt Nanofabrication Center. And by the way, one of those systems was shipped to NQCC the day before yesterday. Right, so many is fine as far as sensors are concerned. Then we can make them deployable. And this is example of atomic clocks. So atomic clocks can be miniaturized. You can deploy such a system on a ship or on a plane. And this is, by the way, not to scale. The ship is the largest. Is the largest ship in the UK, right? Okay, so we can also make them small, really small. So this is an example of a NIST, the American NMI development of a chip-scale atomic clock, and again, the peanut is just for scale. It's not a part of the clock itself. But interestingly, this particular type of the clock is exactly the same as the Essen clock developed in 1955 at NPL, but shrunk to a peanut size. Right, so we can also make them connected. And Peter mentioned the NTC program coordinated by NPL. which aims at building the UK's first national distributed time infrastructure, which is independent of GPS. Now, when it comes to large systems and entangled systems in particular, the problem of scalability is much more severe. So this is again an example of clocks. So theoretically, you can say even a modest size entangled ensemble of, say, 10 entangled ions can give you a very tangible advantage when it comes to uncertainty or time at which you arrive at a certain level of target level of uncertainty. However, in reality, we have to deal with noise and decoherence, and this is what is illustrated here. So very quickly, as you increase the size of the entangled system, you lose contrast. So the amplitude of these oscillations are no longer the same. They go small and small and small. You still can get advantage, which is visible here through the more rapid oscillations of the Ramsey fringes as you go to n atoms, n times more oscillations, so you can gain the advantage this way. But if you scale this up, the amplitude goes down, so you do not get advantage as quickly as you might. And so the conclusion of this example is that we need to scale not just the number of qubits, but their quality at the same time. And quality means coherence, performance, connectivity, and so on. So this is certainly true for quantum computers. And I put this slide because I know that Sir Peter likes it. And what it basically shows you is that if you only increase the number of qubits, you do not climb the mountain, the mountain which leads you to the promised land of fault-tolerant quantum computing. If you just increase the coherence time or some other metrics of error rate, you are still at the hill. At the foot of the hill. You need to do both at the same time. And still recently, we've seen that, in particular with superconducting systems, we're making a rather substantial progress. So the quantum error correction threshold was achieved, for example, by Google. They published it in 2 papers. And IBM released more than 1,000 qubit quantum computer also 2 years ago. So we are going somewhere, but still this problem remains the same. We need to increase the size and improve the quality of individual qubits at the same time. Okay, so superconducting quantum computers. They certainly make most headlines. I like this quote from Rolf Landauer that this proposal will, for quantum computation, will certainly fail because of noise. And I think he's almost right, because noise is the most significant problem that we face. And this problem becomes more severe as the size of the computer is increased. So let's look at this. So this is the Nature reflection on the IBM announcement of a 1,000-qubit quantum computer. Look at the top. the company will now focus on developing smaller, more reliable processes. And I think it tells you some story. So what's the problem? The problem, almost everyone agrees, is incidental two-level systems that are present in the material surrounding qubits, mostly in dielectrics. So you can see it in the size of the error bars on various qubits of an early IBM computer. You can see it also in these wiggly lines measured by Google, and each line is essentially a failure of a qubit, and you see it wiggles like this over time, so it represents an additional problem. And this is our hero qubit fabricated at Superfab at Royal Holloway. You see it has a coherence time, relaxation time of about 300 microseconds, but the histogram is very wide. So basically, interaction of qubits, our man-made two-level systems, with these incidental two-level systems lead to reduced coherence time, disable qubits for long periods, and what's even worse is that bigger QPU means bigger problem. Now, we at NPL work in the direction which may help solve some of these problems. We believe that for that we need to develop a very different kind of materials metrology, where we investigate properties of materials in their operational environment, which means 10 millikelvin, 6 gigahertz or so, where qubits as well operate. So here are some developments, here are some directions and relevant papers, but the last, well, the one about scanning microscopy is, I think, the most recent one, where for the first time the team led by Sebastian de Graaf was able to actually see a TLS, see a two-level system, this incidental defect. And I think this is a rather interesting development in this story. And then another paper in Nature Communications about controlling interactions of qubits with these incidental defects by adding quantum fluids such as helium-3 into the fridge. So not only 10 millikelvin, but also helium-3 here. Okay. Let's switch gears a little bit and speak about metrology in support of the quantum industry. And when we talk about using or investing in quantum, what are the questions that we really want to ask? Does it work? Is it better than something else? What's the cost? Where to get it? And is it safe and secure? All right? So with all these questions in mind, we at NPL set up a program which aims to support the quantum industry, not only the quantum companies, but also the supply chain companies. And we do it based on our expertise of, 70 years or so of working with quantum, developing quantum standards for the realization of SI units. And this program covers all the way from materials to constant computation, sensors, and of course clocks. We have a particular element of this program which is called Measurement for Quantum, which provides free specialist measurement expertise to UK companies. And I think those dots, about 30 of them, are from last year alone. So these are the companies that use this facility to support their innovation. We collaborate very extensively, both in the UK and internationally. And of all these collaborations, I would particularly emphasize the collaboration with national measurement institutes around the world. So it's a large network. Almost every country has its own NMI. So we worked with NIST, we worked with PCB in Germany, NMIJ in Japan, CRIS in Korea, and so on and so on. So we are also a part of the European Meteorology Network, and Tobias Lindström is over there. There is one particular activity in the EMNQ, European Meteorology Network for Quantum, which is relevant to this session, and that looks at how meteorology should develop and scale as the quantum technology develops and scales at the same time. Okay, so standards we lead together with UK Quantum, BSI, and other organizations on the UK Standards Network. At the moment, we have the pilot, and I think standardization is a tricky business. It's long-term, and it cannot be premature, so not to stifle innovation. But in the end of the day, this is what gives confidence in the use of quantum technologies. Just a couple of examples of supporting the supply chain. So cryogenic quantum computing, we spoke about superconductors, but there is also spin qubits operating at cryogenic temperatures. So you need to be able to reliably characterize all these components and subsystems. This is tricky because you can use a qubit itself as your reference when it comes to one. When you have many thousands, you better know your system very well. Another example is characterization of photonic devices, and this includes detectors and emitters and quantum random number generators and so on and so forth. And this is probably the one side of quantum technology that is starting to be standardized. So we contributed to all these many standards, in particular on quantum key distribution. And last example, NMIs around the world, and NPL is not an exception, are now asked questions that are tricky, such as which quantum computer is the best. And we, of course, don't know the answer to this question, but at least we can provide some guidance around the metrics that can be used to compare different kinds of quantum computers. And I particularly encourage you to look at this paper, which is written by NPL and NQCC and Riverlane and others, which summarizes some of the existing metrics and gives you guidance on how to applied in practice. So this is my very last slide. Quantum technologies are already scaling up. It's not the case that we don't know how to do it. But certainly quantum computing and other technologies relying on entangled mass scale much further become useful. Metrology can help you along the way. And if you want to know more about NMI role in this whole story, this is the paper that we recently wrote with colleagues from other NMIs. Thank you.
Okay, I'd like to invite Alex and Carmen to come back to stage. And so yeah, put your hand up if you've got questions. So Peter.
It's on scaling, in fact, for monolithic devices. And you talk quite a lot, all three of you, about that. Early results from SLAC, Wisconsin, and Fermilab demonstrated that cosmic ray shard, the muons, created a phonon cascade which caused correlated errors on the chip. And as far as I'm aware, there are no known quantum error correction techniques that work for correlated errors. Is this the death of monolithic machines?
I can start. To take us out of the death trap set up by... whilst there is no, and I mean, what you say is absolutely true, but equally we are working on new types of error correction. And I cannot disclose much of that story here, because that's still work in progress. But bringing that different type of scalability requires different type of error correction, or adoption of the error correction that we currently use. So definitely that's on the roadmap, and I skipped that part of the story because I wanted to focus primarily on the message that we do need to build the supply chain first place, because without that, that error correction is not going to be useful.
I can say a few words. Yes, so muons and ionizing radiation indeed cause this shower of quasi-particles which reset the qubits. So now it was shown quite recently that there is a length scale at which this happens. And this is similar to maybe 300 micrometers or so. So if you can have your wafer large enough, then you may be fine. You may store the information in qubits elsewhere. This one. Second, I think what would be very interesting is to perform experiments in the underground, such as Bowlby. And Bowlby in particular, because it has low ionizing radiation background compared to, let's say, Gran Sasso in Italy. So that would be great. And then, if it helps, then let's put our quantum computers in deep mines. After all, how many do we need?
Yeah, so to your question of, is this the death of monolithic scaling? I don't think monolithic scaling will ever die. We always need, better and larger QPUs, and for quantum, better is better, but it's just not the whole story. I think we can learn a lot from the history of CPU and GPU scaling, where there's always there's always better processors being made and better ways to aggregate them. And in quantum, that aggregation is perhaps even more important because of what we've heard in the sessions today, but also because ultimately the way you aggregate the computers, the way you entangle them together really dictates the architecture of the computer and how you ultimately do quantum error correction. And so really, for quantum, the network is the computer. But that doesn't mean the death of monolithic scaling. Again, better is better.
Okay, thank you. Another question? No other questions? Matt, right to the back.
Hi there. This is for Carmen, mostly, I think. We talk about error correction efficiency, about the number of qubits, but often overlooked is the speed of the error correction code. Is there a potential advantage in your network technology for using the high data rate of the technology to support that?
Yes, I'm glad you asked that. Yes, there is, and we're working on a paper on that soon. So some of our recent results show that even if we say work with a distributed quantum computing system made of ions, but then we carry out distributed quantum error correction, so the logical qubits happen across the whole system, and actually it may just be that the way you carry out the logical operations is via reconfiguring that photonic switching network, and that's faster than the ion. So it may just be that by having this sort of architecture, you can definitely not bring down the gate speed, but even potentially increase it in some cases. But yeah, coming up this year probably.
Okay, thank you. So any other questions? One in the middle there.
To Professor Talanchuk, what, in your opinion, is the highest priority for new standards in quantum technology?
Terminology. I think we need to ensure that people understand the same thing when they use quantum terms. And I think the whole history of standardization of emerging technologies, such as nanotechnology in the past, tells us that this is going to be the first and perhaps the most critical step towards wider standardization. So the use of words is important, and I think even when it comes to benchmarking and algorithms, benchmarking different computers and algorithms, we often find that people use the same thing in different, describe the same thing in different words, and also they use the same words for very different things, and I think this is very unhelpful. So some degree of uniformity is needed, and this will be done through standardization, I believe.
Okay, I think we've got time for one more question. No? Everybody wants coffee? Okay, so let's thank all the speakers again. And Kaylee, we have a 30-minute break? Yeah. Okay.
Where's Elodie?
Yeah. Hello, everyone. If you can take your seats, we'll get started with the panel discussion. Okay. My name is Roberto Desimoni. I'm going to be chairing this panel discussion, which is going to take about an hour and 5-10 minutes. I'm going to bring my four panelists. I'm going to bring my four panelists up to the stage, and then I'll introduce the whole session. So if the four panelists can come up and have seats beside me. So we've got representatives from 2 quantum companies, from academia, and from an industry association. I'll let them introduce themselves in a second. As I said, my name's Roberto Desimoni. I've been involved in AI for the last 40 years, and for the last 10 years, I've been involved in exploiting quantum. So I've worked on lots of programs to do with the military, and defense, security, financial services. But over the last 10 years, I've been looking at the commercialization of quantum, doing a number of different feasibility studies for MOD and other bodies on cybersecurity, on communications, on military command and control, and intelligence and surveillance, a whole bunch of different things. So what we're going to do today is we're going to explore the issue of quantum innovation, and in particular, what support is needed to scale up the kind of innovation that we're all desiring? It's actually the same question that was asked about 5 or 6 years ago by Patrick Vallance. He'd organized a round table in 2019 and invited 9 people from industry. Jonathan was one of them, and there's a few others who are here, a few academics, quantum academics and quantum startups, but he also had 2 permanent secretaries and 5 senior policy advisors. This is 2019, the end of phase 1. We knew the money was for phase 2, and he wanted to ask us this question. So we're giving you this money. What else do we need to do to support the kind of innovation that we really desire? That's what we're going to focus on in this panel discussion. Right, let me now go through. I'll start at the end. Ilias, about a minute, just who you are, what your role is, and what you do.
Hi, my name's Ilias, and I'm the Chief Product Officer at a company called Quantinuum, which is the result of a merger or a combination of what was Cambridge Quantum Computing and what was Honeywell Quantum Solutions, a division within Honeywell on the hardware side. My job is primarily to be responsible for the delivery of the roadmap. We have an integrated roadmap, which is largely in the public domain. All of the technical teams ultimately report into me, and I also have responsibility for the budget now with our global partnerships that are beginning to commercialize quantum. The only other thing I would say is that we're fairly widely distributed. Our primary fabrication business is in Colorado. In Broomfield, many of you will know just how seriously Colorado is taking quantum. We have an important base up in Minnesota. We have our own fab, although we're moving to Infineon very soon. The Cambridge campus here in the United Kingdom is primarily on the chemistry side. We also have a strong middleware team where we've just created a platform, and then we've got outposts in Munich and in Japan, and I'll leave it at that. Thank you.
Jonathan.
Thank you. Jonathan Lee Smith. I'm the Executive Director for UK Quantum. We're the association for the UK's quantum industry. Just over 2 years old now, and about 60 members. So I'd say all of the industry representatives here and earlier on today are members. So we obviously work very closely with government and UKRI, helping encourage the development of the delivery plan for the next phase of the National Quantum Technologies Programme. But we also work on topics such as export control with Department for Business and Trade, standards, which Alex referred to, and the quantum standards pilots. We work very closely with Tech UK and the NQCC on responsible innovation, which I hope we'll be able to touch on a little bit later, and of course, skills as well. Thank you.
Great. Eleni.
Hello, everyone. It's a real pleasure to be here. So my name is Eleni Diamanti. I'm a CNRS Research Director at Sorbonne University in Paris, in France. So I lead an experimental group in quantum communication and cryptography. Additionally, I direct the Paris Quantum Technologies Center, which is a hub for including quantum innovation and academics, bringing together research and industry community in France. And then at the European level, I also am part of the Strategic Advisory Board of the Quantum Technologies Flagship Project, and I'm also co-chairing the working group on infrastructure that I think is among the topics that we're going to discuss today for the Quantum Technologies Coordination Group. This is yet another European Commission group that will feed strategies to the upcoming EU Quantum Act. So maybe we can talk about that as well. So additionally to all of this, policy and academic responsibilities, I'm also co-founder and scientific advisor of the quantum interconnect company WeLink, that is based in Paris in France. So I'll be very glad to discuss about all these aspects, policy, academic research, and entrepreneurship in this panel. Thank you.
Great. Before I introduce Steve, we were going to have a different panel member, Andrew Shields from Toshiba Europe, but unfortunately he's not feeling well today and wasn't able to come. Steve happily jumped in. So let's give Steve a chance to introduce himself.
Happy to be the backup for Andrew. Steve Riley, CEO and founder of Riverlane. Riverlane helps quantum computing companies solve error correction. Essentially, we are a classical semiconductor company building the chips that are needed to scale up quantum computers. Our customers are based around the world, so we supply companies in the US, in Europe, in Japan. We supply around half of the world's quantum computing companies, and are about 100 people based largely out of Cambridge, UK.
Great. Okay, so what we're going to do now, we're going to have two sort of Q&A sessions. I'm going to do a Q&A with the four panelists for about 35, 40 minutes, and then we're going to open it up to the audience for your questions, and also from Slido, if I get any here. We're going to cover a few topics, but not too many. So the ones we're probably going to cover in the next 30 minutes will be to do with funding and international collaboration, infrastructure and standards, and regulation and ethics, including responsible innovation. If we've got more time, we'll cover some other topics, but I'm sure others would want to pick up on those. So let's start with funding and international collaboration. So my first question is the right kind of funding available here in the UK and elsewhere to support the kind of innovation we're hearing from in big, broad national programs? From many sources, from government, from venture capitalists, from industry. Ilyas, what are your thoughts on, is this the right kind of funding? Are we getting the right kind of funding to support what we need?
Well, you started, Roberto, with a very direct question, is it available? And the summary answer, in my opinion, is yes. And I think that there are three areas that are beginning to open up. I'm not suggesting it's easy, but it certainly is available. So just from the point of view of context, at Quantinuum, we've raised and largely spent about $2 billion. And with the exception of 100 million of that, it's all been from what I would call strategic investors who are corporates, who typically know more than we do about the reasons they're investing, and who have an alignment of interest with the fact that useful quantum computers, even today, are still a few years away. We happen to think 5 or 6 years away. And that alignment of interest arises, I think, sometimes by accident and sometimes very deliberately when governments get involved. So in terms of the history of where we have raised money, we have avoided and managed largely to avoid financial capital. I do think financial capital is available, and Stephen's fantastic stand-in because he's far more experienced than most others in that particular area. The main thing that I think we're looking at from a transition standpoint is that we are now looking at the allocation of relatively large amounts of money from governments who are no longer channeling that money through third-party research institutions, for example, in the United States like IARPA and DARPA. We have benefited from that as a company. I didn't include that in our 2 billion. But that is opening up in Singapore, in Japan, in Germany, in the United States in particular, in Denmark, in France, you name it, Saudi Arabia. There's no economy of note that doesn't have a quantum program where they're stepping out of funding research and into funding ecosystems and hubs and the acquisition of machines. So that's not investment, that's genuine purchase orders, if you like. And those things are high-octane energy for our industry. It's the same as the research programs that the government gave 10 years ago, 5 years ago, 3 years ago, which allowed the pump priming. And I think that the vision that people had who set that pump priming is now coming to bear fruit, because these large governments are being convinced, either directly or indirectly. If it's indirectly, it'll be through a company, so in Saudi Arabia through Aramco, etc., etc., etc. In our case, we announced a big deal with SoftBank 2 weeks ago, and that, of course, is half and half. Some of it's government money, some of it is SoftBank's own money. The last point I'll make is that I still think that there is a challenge in getting any revenue which is recurrent because most revenue that is being reported is the rechanneling of government research funding. And once that happens, once there is some recurrent revenue which can be qualitatively analysed and objectively pointed to by people who are not the company, because the company always says, oh, we've got this revenue. So when other people start saying that's revenue, then of course I think financial investors, that is a huge, huge apron that will become available, and I'm hoping that that is now starting to happen. It's not there yet, but it will happen. I discount here the urge of the masses to jump into things. So we've all seen what's happened to the publicly listed companies, and you can have your views on that, whichever way you want to. If you're raising money, you'll point to them and say, oh, I'm worth at least as much as they are. But if you disregard that, which is largely retail, I do think that high-quality private money is beginning to take an interest in backing things which are still 2 to 3 years away from revenue. So that's my perspective.
Jonathan, in your role with UK Quantum, engaging with lots of companies that are now playing or want to play in the area, what are you seeing in terms of their strong design interest and their ability to put their hands in their pockets and sort of take some money out and stimulate and fund some of that work? You've probably got good views on this.
Well, so speaking to about the general quantum companies, I wouldn't say the money is readily available in the UK. I think the majority of people are agonising about where the private investment comes from within the UK, perhaps available internationally, but that brings other issues and pressures to, well, what happens to a UK company then if they're taking the majority of their money from elsewhere? And that's a live discussion, I think. And also, I guess we have to be realistic that we are all looking forward to seeing how much the government is going to be investing in quantum. The commitment we heard was from a couple of years ago now in the previous administration, and as yet we do not know how much is going to be invested. So we don't know what that side of the equation looks like as well. So I think, you know, all of these are still nervous times at the moment, certainly for the next year, bearing in mind we've got a 2-phase spending review coming, and I'm not sure we can hold out much hope for this year.
Okay. Eleni, I'm not going to ask you the same question because I want to switch it a little bit, unless you wanted to add something to that.
I had a little comment on this. I agree with what you said. I'm kind of aligned with Jonathan. I think it's kind of a bit tense moments right now. So we do lag in Europe behind a bit in funding, in private funding, depending with respect, in particular, when we compare with the US. So I would think that what we need to do possibly is, I think governments are doing their best with the national programs, like Ilya said, and everything. They should adopt quantum technologies, probably the first to show the way. And then we may want to think about new ways to find funding synergies between the private and the public world to de-risk the investment in quantum industry. Because I believe there is a kind of, don't know if it's going to bring revenue, exactly, the market, how close or far it is. So somehow, some sort of synergies in this way, I think would be helpful.
Okay. Steve, I'm going to switch the question slightly differently. It's more about international collaborations. And certainly with the work you presented earlier on quantum error correction, you've been collaborating with many teams across the world. How strong are international collaborations for quantum innovation work? What do you see in this area? And what are good examples?
Yeah, I think it's hugely fluid. I mean, certainly we work with colleagues in the US and in Europe. I think that comes from where quantum was perhaps 5-10 years ago. It's quite a small community. A lot of the people who are now running teams in the US were previously here in London. So I think this kind of college of people with strong roots to the UK has resulted in very strong collaborations. I mean, we work with companies that are based in the US. So the results I presented were with Rigetti, so that was their team on the West Coast. People are interested in working with the best people they possibly can, right? And the centers of excellence are different around the world. So Riverlane is based in Cambridge because Cambridge has a huge number of chip design expertise. So ARM is headquartered in Cambridge, and that's resulted in this massive skill base that we are leveraging. There are only a few other places in the world that have that level of skill. You know, they're in the Bay Area or they're in Texas, but Cambridge is one of the top places in the world. So people, you know, that enables then the kind of the best people to work on the most interesting problems. So I think it's absolutely vital. I think this is a humanity scale problem. Clearly there are some countries we're not collaborating with right now because of geopolitics, but frankly, I think we have to collaborate. And I think the strength of the ecosystem is because of that international collaboration.
Okay. Ellen, did you want to add on that? Because you're heavily involved at an EU level in many collaborations.
Indeed, and it's a subject very close to my heart, international collaboration. And I think we need to acknowledge here, we should not hide from the fact that this is a very strategic matter. So quantum technologies have become a strategic topic, and they depend a lot on geopolitical tensions. Up till now, the line was, in general, the framework, we work with like-minded countries. In EU, for example, they share EU values, so this is what we call like-minded countries, but nowadays it's not completely sure, even like-minded countries, what it means. Like previous alliances start to break down, so it's a bit volatile. We're a bit in a volatile situation, and I think quantum technologies investment and collaboration may suffer from this. Okay. And I think we're not going to do it alone. I completely agree. This is going to be an international topic. So I think the question is, how can we collaborate? There are some good, successful examples. For example, of I can highlight the EU. For example, has is opening up joint calls on quantum technologies with right now opening in South Korea with Japan. There is open now. There is a lot of talking with Canada. There is even bilateral agreements between countries. There is an open call, for example, between the French National Research Agency and NSF in the US right now, including in quantum. Okay, so there is a real effort for bringing things together. But concretely, what does it mean to collaborate today? For me, it means at the very least sharing information. Okay. At even further away, aligning policy frameworks, although this looks a little bit ambitious, but it could be an option. It could go even further away to trade alignment for some like-minded countries in quantum technologies. And it all depends if we manage to do this, and I think we have to.
Okay. Jonathan, so you head UK Quantum. It's been around for 2 years. Are there other similar industry associations in other countries in the quantum area? And if so, do you engage with them? What do you do?
Certainly there are. I mean, the big ones, of course, are QEDC in the US, QUIC in mainland Europe, QSTAR in Japan. But you'll also see a lot of nations, and QIC in Canada as well. Quite a few nations have developing associations as well, but maybe not quite as sort of established as us. And yes, we collaborate and talk all the time. Elena was talking about the geopolitical tensions. We all know this is an international endeavour. One of the things we talk about is how we can ensure, on behalf of industry, that government are in fact representing the position that we would expect, and they don't get locked in other sorts of conversations. Things like standards, for example, we coordinate behind the scenes just to make sure that we don't see unintentioned positions sort of playing out. Associations, we talk a lot. We have a very strong overlapping membership as well, and so that's
great. We'll come back to standards soon, actually. Let me just switch a little bit. Ilyas, infrastructure. What infrastructure is needed to support the kind of quantum innovation programs that we designed? We've heard of the quantum internet, the dark fiber, cloud computing. What else is actually needed to really stimulate and support innovation?
I'm actually slightly going to cheat and use my 2 minutes to go back on something specific, if I may, Roberto. You're a very indulgent chairman, well, at least for the next minute anyway. Look, I think that we need to put some flesh on the bones about the specifics of funding. Otherwise, I'm not sure the audience gets very far. So let me be specific. In the United States, I think the flipping of the switch happened last year. And Colorado, Illinois, New Mexico, Connecticut, at minimum, and probably 1 or 2 states thereafter, which will be announced very shortly, have significant amounts of money that have now been delegated to them, and they are spending it. And that spending is much easier to access administratively. We've all been through the agonies of the flagship program in Europe, or at least I'm sure most of us have. And I'm not saying it's a walk in the park, but it doesn't matter where you are. If you want to be in any of those states, the approachability, the simplicity, and the ease with which funding in meaningful ways can be released is refreshing. And I think it's really important that we recognize that. It's so easy to just bellyache all the time. And I know there's at least 2 UK companies that have taken, I don't know if anybody from Ionics is here, but they've just set up in Broomfield or in Boulder. There you are. And so these things do exist. I also want to bring to your attention the deep and meaningful financial commitment that has been dispersed by Bavaria, never mind Germany. And as a British company, it is relatively straightforward to benefit from real cash and not just these sort of matching loans and whatever. And the way in which the Bavarian program is managed, coming back to infrastructure, actually ties in industrial engagement. So our biggest source of revenue from an industrial is actually BMW, and it's a 5-year program. We've been on it for 5 years, and there's another 3 years to go, and it's millions of quid. So these are not just figments of one's imagination. And I'll finish on the RICAM program. I think some of you are involved. I know Steve's involved in Japan a lot. But these programs now are beginning to be a lot more accessible than they were. And I think, Jonathan, your point about, what comes with it, if you give away equity, well, of course, you're going to be diluted, and that's got with it all kinds of agonies that, I won't talk about. We're still 45% owned by Brits, despite all the money we've raised. And every single dollar I've just referred to is non-dilutative, right? So we benefit from hundreds of millions of dollars of funding, we meaning Continuum, that is non-dilutative. And I think that's really important. We have got into that stage now. This is not 2019, this is not 2022. We are in a different phase, maybe not in the United Kingdom for all kinds of reasons, but certainly outside. And I think British firms, for reasons that the collegial impact that Steve mentioned, are right at the forefront. And I'm really glad Ionics is here as a shining example of what can be done with ambition and attention to detail. And Lucas is at the back as well. And people like that, these things really, really do matter. And that money is available. I'm sorry if Jonathan and Eleni don't agree. I'm telling you from first-hand experience that it is there.
Okay. Infrastructure. I'm going to come to Eleni, because I know this is a topic that you wanted to address. Tell us more about what is needed to support.
So maybe we can talk about what is infrastructure, first of all.
What is it?
So for example, in the continent, in Europe, we are the 4 lines of infrastructure we're talking to, just to make sure that we all are on the same page, is first of all the quantum computing infrastructure, where by this we mean that we have access to QPUs, right, to devices, integration in HPC framework and the corresponding use cases. So this is one infrastructure where a challenge in Europe is to align the big European quantum computing infrastructure with regional and national, which is interesting because Elias mentioned Bavaria. So region and national projects need to be aligned with the whole European one. And why not the rest? I'm going to mention something. Actually, in quantum computing, there is also a tendency to go towards quantum computing excellence centers, and there is in Europe. And for example, there, and they are meant to be for collaborative research in programming ecosystem, okay? And for example, we can totally imagine a collaboration with NQCC, and I think we should just do it. right? So this is a way of working together, for example. Then there is the European quantum communication infrastructure. So this is in quantum communication, the quantum internet, where we can also see a path for deploying an infrastructure at the global scale. Then there is sensing and metrology infrastructure that is being pushed as well in Europe and worldwide. And fourth is the chips manufacturing infrastructure, which is extremely important, of huge strategic relevance, obviously, regarding supply chain and resilience in supply chain and autonomy in supply chain, and where there are pilot lines for moving this, for pushing this infrastructure. So all of these infrastructures are kind of coexist and need to lead to innovation, right? And so what you are asking is what we need to do. What is missing in them already? So these pilot lines that we're doing in Europe, for example, I think is a good way to forward for this type of infrastructures. What we need to do is to facilitate access of the industry, including startups and SMEs, for example, to the quantum computing infrastructure. Or to the chips manufacturing pilot lines, right? Be imaginative in ways on how to access this infrastructure in an easier way, because this will lead, if all of these companies, including of course academic groups, have access to this infrastructure, this will lead to more innovation, right? And then alignment of all of this innovation with end user needs. This is really what is missing in some cases. So to actually make this infrastructure, direct them towards real services and needs that can actually be used for applications. These are two possible paths using the infrastructure.
Okay. Cloud computing. Now, I know that's not so much your area, but being able to access a whole set of different types of error correction techniques, like a quiz kit for quantum error correction and all the other types of approaches to correction to support fault-tolerant computing. What are you seeing happening in terms of building that kind of infrastructure, following on from your area?
Yeah, I think it's a really exciting time. I remember back in 2018, the first quantum computers were made available on the cloud, and they were pretty janky, like 5 qubits. But it was cool because you could then experiment, and it really, I think, created an awareness in a community that was much bigger than the quantum computing community. So software developers started getting interested in quantum computing, and the tools were there so that they could learn about how to program a quantum computer and quantum computing in general. So the sort of software development kits and the education tools enabled a whole community of people to upskill on quantum computing, and indeed, Qiskit was remarkably successful. I think there are like 1 million people who access those tools. So Liz Durst built that team, and I think there's a huge amount of credit that's due to that team. I mean, it's become the most popular approach to quantum computing, and to be honest, a little bit surprising. I mean, IBM's not necessarily known for being the best software company in the world. At the time, there were Microsoft and Google were all building similar software development kits, but it was Qiskit that won. And I think the reason was the openness and the education that went alongside it. So fast forward to today, and I think we have the same situation. We have the first quantum computers that are capable of error correction. So there's an opportunity to build the tools and the education around error correction and create a user community exploring how best to implement error correcting codes. And indeed, we just hired Liz Durst to do that. So plugging a bit Riverlane. But yeah, so I think this is really exciting. I think in the next few years, we're going to be experimenting with how best to do logic on quantum computers. And I would love to enable as many people as possible to do that.
Great. I'm going to switch things onto standards now. So I've been heavily involved in the defense industry and other industry where standards are absolutely critical. So how important are standards for quantum innovation? And what kind of standards are being developed now that maybe you're involved with? Just looking at you, Jonathan, because I know you raised it earlier on.
Sure. But before that...
Oh, okay.
No, and I will take 30 seconds on that. So, respecting what you've just said, I guess if your comment, Elias, to companies that there is money out there, and the non-dilutive bit is obviously important, I wouldn't translate into government, therefore there's nothing to worry about in the UK. That would be my reaction against it. There is a lot that needs to be done in the UK to make sure the right sort of capital and investment is made. I wouldn't dispute if you set your eyes out, there is money there. Good. So standards are critical. I mean, my background is telecoms, and telecoms runs on standards. So I'm quite familiar with that. Indeed, I was head of standards for BT for a number of years. If we look at the quantum, it is nascent, shall we say. And part of the reason for the UK quantum standards pilot network is to help stimulate engagement and create the right sort of pathways in. There is a lot of work going on, particularly around, in the telecoms area, QKD, which is unfortunate given we're in the UK, but they know how to go about doing standards, so you'll see that in ETSI and you'll see it in the ITU. Otherwise, going back to talking to my counterparts in other associations, it's actually quite hard to get industry involved in standards activities, and I think largely because people aren't quite sure what it is they want to standardise yet. But we've heard throughout the morning the importance of sorting out the supply chain. Well, one way of doing that is to create a market for the supply chain, because normally they follow themselves. But if you haven't, how can you help create the market? It is to actually fix on what it is you're asking them to provide. And one way of doing that, often the critical way of doing that, is setting key standards so that suppliers know what it is they're providing and know there'll be more than one customer who's going to buy this thing. Because if the customers can't agree on it, what is the market that the supply chain is supposed to be adjacent at? So that's quite common in the telecoms. The same goes for customers. Customers, I guess it's very early stages, and so it's explorative. But by and large, when people are buying operational technologies, they don't like bespoke products. They don't like suppliers of one. And that, again, is where standards come about. And there's also a lot of interoperability. We've heard of bits and pieces around networking in data centers and what have you. True, if you're going to integrate components, those usually are a target for standards that allow the different parties to agree on what it is they're going to do. But it is quite nascent at the moment.
Elias, who are driving standards at the moment? Does it, in quantum, does it depend on which area of quantum you're in? Who's driving the standards at the moment?
Yeah, well, it is national agencies, obviously. And we've not yet got to that point where the collaborators, apart from in cryptography, so we have quite a deep team on cybersecurity and cryptography, where we're beginning to see NIST take a bit of a lead. I was at that 2019 meeting as well, and remember conversation about this. But the thing that I think I would just switch perspective slightly is not so much standards. I think I agree with Jonathan that it will happen as soon as you get more commercialization and large economic concerns demand that they're not being misled either into silos or into comparing apples and oranges and being told by the vendors, oh, don't worry, it's the same. I think it's more about language in the short term, and I think the larger organizations have a responsibility to become, shall we say, standardized in the way they talk about computational capability now and in the future. So if you look, Roberto, at the 4 or 5 public roadmaps on the hardware side, Microsoft just dropped something this morning. I don't think it changes their roadmap, but it's the first time that the QBI program has stimulated. This is the United States QBI program, which I think all of you are aware of, will drive a standard towards what useful utility scale means. So it's the language around that. The only other point I would make is that one of the best decisions I ever made, and I think still, I mean, if I had I don't have a tattoo, but if I did, it'd be a Union Bloody Jack. I have to fly. I think we have a responsibility to fly the flag wherever we go. And I think that we are such a powerhouse in quantum, and we sometimes forget it, and we keep contemplating our naval. the view of the United Kingdom programme is so much more robust outside of the United Kingdom than it actually is in the United Kingdom. Companies like Riverlane, Ionics, and people like Professor Lucas, and there are many others I've mentioned, Phasecraft, etc. I think we really do carry that flag. So the language we use very quickly gets adopted. I'll finish by saying that in the best decision I've made was 2021, I think it was, we open source something called Ticket, which is a software development platform. We now have around the world 3.5 million, coming up to 3.6 million downloads. On average, each download sustains 10 users. In some universities, it's more. So the average is about 10. That's 30 million people around the world who are using a British product in the open source that is defining some of the standards, both in compilation and hopefully ultimately in accessing the applications that can then be platform agnostic or platform neutral. And I think we sometimes forget that these foundational steps that were taken early on lead to future standardization, both of language as well. I wouldn't really have anything meaningful to add in the other areas. I think the experts have a much better opinion. But I would say cybersecurity is a place where we're getting closer and closer.
So I'm going to sort of take us related to standards, but in systems engineering. I'm involved at Loughborough University in their quantum systems engineering program. And in fact, in COSI, which is I think it's the International Committee for Systems Engineering, is just about to set up a working group in quantum. And there's two people in the audience who helped encourage them to do that, Mark Everett and Kieran Bergstrom from Loughborough. So a question I've got is, how much is being to understand how complex hybrid quantum classical solutions can be engineered and tested and evaluated and maybe at some point certified? Is there enough being done in this area under the current program to take our quantum system engineering hybrid up to a level where we really can put systems together? You know, my question about dynamic reconfigurable. Any thoughts on that?
Yeah, maybe I could take that one. So it's a central part of DARPA's quantum benchmarking initiative. So this is the program to essentially develop the evidence to make a purchasing decision of a large-scale quantum computer. So do you have a viable approach to building a quantum computer is the central question. Feels like it's either yes and you believe the hype, or no and these are either going to be impossible to build or they're going to be completely useless. And so this program's designed to answer that question. And it takes essentially three approaches. One, of course, is physics. You know, does the physics make sense? But the second one is systems engineering. So what does the whole system look like at scale? What are the subsystems? And what is happening to hammer down on the key risks in each of those subsystems? And I think this is a great approach. It requires a lot of skill on the evaluation and testing side, and DARPA's program is going to be very large. There'll be, I think, there will be hundreds of people working on the test and evaluation side. So it takes skill and experience to do that. And this is, I think, a great example where quantum computing can learn from other fields, from other disciplines, and bring those skills into quantum computing, because we're now at the stage where this is a critical part of scaling up.
Steve, on that QBI program, I think if I'm not mistaken, there's a healthy disproportion of non-US companies that have made the cut, which I think is also to the credit of the DARPA program. I'm sure you must have, I don't think you guys were directly involved, but I think that is a really good sign, in my opinion. I think 2 years ago, we perhaps wouldn't have been able to say that.
Yeah. Eleni, did you want to add anything to this?
I can add that, yeah, benchmarking is extremely important. Part of my research has been in QKD, and so I've followed how hard it is already for such a well-established technology to do standards. The very first QKD product was certified very recently after years and years and years of work, and so the link between standards and certification is a long path as well. so in Europe, we have a very wide-scale certification project as well in quantum cryptography. So what I can say, we can learn from this, which is a bit what you said, Jonathan, for quantum computing as well. And I think indeed, identify the correct benchmarks and key performance indicators is the very, very first step. So what do we want to standardize, right? And do we all agree in it? There's so many standardization bodies. You talk yet another working group. There's about, I don't know how many working groups in different standardization bodies. So it's a full-time job if one wants to look into standards. So I think it will be a long effort how you define utility scale quantum computer, how you define cryptographically relevant quantum computer, how do you find, integrate hybrid with HPC. So identifying already relevant benchmarks and key performance indicators is already the very first step. And for this, we need experts in this field to identify them and work on them. And this is something I think we can collaborate on in many, across continents.
Jonathan, I'm going to come to an area you highlighted earlier on, which was responsible innovation and relates to a whole area issues of regulation and ethics. What efforts are in place now to address ethical concerns about innovation with quantum-enabled systems? And is enough being done?
There is more to be done, but certainly within the UK, it was recognised across industry quite a few years ago that we really did need to lean into how we approached innovation and the development and use of quantum technologies. And so, very recently, just at the end of last year, a collaboration called the Responsible Quantum Industry Forum published its first set of principles for responsible innovation in quantum. Nothing overly dramatic, but what was critical there was that it was industry, and that was represented by Tech UK, and I'm delighted that Laura Foster is in the room. We had Claudia Perry from BP representing UK Quantum, she's over there, but actually led by a lady called Natasha Alton from the NQCC, and I don't think Natasha is here, which is unfortunate, because she's been really the force behind it. But this was industry getting together to work out what its first draft set of principles would be and putting them out on the table, rather than being pushed and forced into doing it, which was largely what we saw with AI. Since then, we've seen them actually being recommended as part of the regulatory framework in the UK by the Regulatory Horizons Council's report, which was then accepted by the Office for Quantum. So right now, we're in a very strong position. Apart from that was the easy bit, because writing out the principles, and the reason we wanted to just get on and do it was because for a business to actually internalize them and actually put them into practice is really quite hard. What are the practices? What are the business processes? What are the values that a business ought to be expressing to demonstrate and actually enact that? That can be quite challenging. And most quantum industry, most quantum businesses do not have people dedicated to this task, because that's really what we're working on at the moment. So you'll find it getting talked about globally, but I do believe within the UK, actual industry, the UK's industry coming together. When I say UK industry, I mean all of the foreign companies who are operating in the UK as well. That, I think, puts us ahead.
So in AI, I've been involved with the all-party parliamentary group on AI, which addresses ethics and regulation issues. It's about informing parliamentarians about AI, but they help stimulate the growth of the AI Council and also the Centre for Data Ethics and Innovation, which could be used in multiple different technology areas. I think I'm going to leave that open to other questions from the audience you might want to probe in more detail. We spent about 35 minutes on this sort of open discussion with the panelists and me. I want to open up to the audience, but let me highlight things that topics we haven't really addressed. We haven't gone into applications and what types of novel applications should we be expecting in the future. We haven't addressed any issues to do with skills and training. Have we got the right kind of people? What are we doing to ensure we get the right people? And also, what kind of missions and grand challenges? I've been involved in DARPA programs since the 90s during Operation Desert Storm. We've got a mission statement from 2023. So maybe there might be some questions along those lines or any other areas. I'm also going to invite those who are online, if you want to send any questions by Slido, I'll pick them up. But I think what we'll do is we'll open up to the audience. So those who have questions, raise your hand, and we'll get a microphone taken to you and get the answer up. Great. Mark.
Thank you for the free plug there, Roberto. For this INCOSE Quantum Systems Engineering Working Group, I'm anxious that we avoid groupthink. So as many people who can contribute as possible would be good. So how could this group best serve the community, and what would we need to do to get organisations to commit person hours to making this something that also best serves the community?
Yeah. Jonathan, did you want to pick up on that one?
Without knowing the details, it's difficult. But I mean, one thing I would note is we are waiting for a report from the Office for Quantum, the output from the skills task force led by Sheila, if Sheila's still in the room. We're waiting for that output, and systems engineering is on the list of core skills that we need to see. So part of it, I think, is on the more details, certainly advertising it out to industry at large, just to make people aware that this is out there. But really, I'd probably ask those who run companies how to do that.
Did anyone else want to add?
Well, just a quick one. I think help explain to systems engineers that quantum computing is A, really interesting, and B, needs their skills.
Okay. Other questions from the audience?
Yeah, thanks. So what I found interesting about this morning's discussion, I think everybody in the room here has been coming to rooms like this for the last 10 years, was the use of the word AI a lot. So my question to, and we all know the reasons for that, but my question to the panel is, do we think, particularly in light of the question up there was what support is needed, do we think that AI is an opportunity for quantum, or is it a threat to quantum?
Okay. Does anyone want to pick that up? I mean, I know I can answer it, but let me see what others. Is AI a threat to quantum?
So AI, I think we've all got to... Sorry, go ahead, Steve.
Yeah, I was just going to say, I mean, AI is very good at taking data and generalizing it. And quantum computers do something very different. They generate new data. So we have a model of the world called quantum mechanics, and it predicts the entire periodic table, properties of materials and molecules and how they interact. That's very powerful. So clearly, if you can generate new data, then you could leverage that to accelerate what you're trying to do in AI. But I think they're quite different, actually.
So I'll add some. Go on.
Yeah, well, yeah, so I think just from a practical standpoint as well, in addition to what Steve has said, we use AI every single day of the week in what we do. And at the moment, we do it to optimize circuits. We have 2 papers out, one with Google DeepMind Group and the other one with Meta, Jan LeCun's group. And we, therefore, are users of AI. In fact, the person who heads up our AI practice is Professor Berman, who is about 3 rows behind you and will be able to articulate in greater detail how we think about AI for quantum. On the quantum for AI side, I think the fact that you're generating new data, which was well articulated by Steve, brings us to a point at the moment of opinion rather than proof. And for what it's worth, our opinion is that AI will benefit from the emergence of this hybrid system, or perhaps even a pure system in time. But if you ask anybody how that might happen, I'm sure you'll get lots of different opinions, including some heated exchanges. For the record, we do have conviction that, yes, the other side will work as well. And again, Ari's around and can explain why we believe that and what it is we're doing. We're very lucky to have in our team a guy called Steve Clark, who was at DeepMind, and something in the public domain is that we're working on Quixer, the first paper's out, which is a quantum transformer. So these are the foundational steps that are needed. Yeah.
I'm going to add something here. So I don't see AI as a threat to quantum at all. I see quantum as an opportunity to put AI on steroids. And we already heard that some of the applications that are currently being done with AI techniques, generative AI neural network, using megawatts of power to generate those solutions could potentially be done with kilowatts of power in quantum-enabled solutions. So I'm not sure that I would take that point. But it's a good point to raise. Anyone else want to add? Otherwise, I'll take another question. Let me take another question. Lee.
Go on, I'll ask the applications question.
Go on.
And I'll make another analogy with GPUs, graphics cards. So GPUs achieved their dominance because they moved away from just doing graphics. And a lot of the examples we've seen this morning have been quantum chemistry. So the question is, will quantum computers ever do more than just quantum mechanics?
Interesting point.
I think my answer is, what do you mean just? Like, we're talking about solving chemistry, like...
Just.
Like, that's huge, and will be transformative. And sure, I don't know all of the specifics, but like, the ability to simulate the world transformed the aerospace industry, right? We've got, and the reason we're able to do that is we have a model of the world, like Navier-Stokes equations, and we have computers that can solve those models. But when you try to do the same for molecular systems, you've got, like Dirac's paper says, and thus we've solved the whole of chemistry and a large part of physics. And the only problem is solving these equations, and I think he's right. Right? And so I think it's kind of, this will be just massive, and I think I wouldn't underappreciate how important this is as a foundational technology. Definitely excited about what else you could do, but I'm happy if we only do that.
Eleni, did you want to add to that?
I can only say that we only see, the low-hanging fruits right now, but there is many, many more to come. But we need to master the technology. I personally, obviously, I'm a bit biased because I work on it, but I believe very much in the applications that will come from the convergence between quantum networking and quantum computing. We heard about it from Carmen before, and I'm very much aligned in this vision. And I think this will boost and scale up even more the capacities of quantum computing, and there we can see the full scale of applications. And the same for the quantum internet. We've been talking a lot about it, there's we're waiting for all these applications. But I think we need to master, advance the technology already, and work on proof of principle, proof of principles, and then further applications will come.
Related to that, you mentioned the word low-hanging fruit, and I would say over the last 10, 15 years, AI has benefited from addressing what I call our low-hanging fruit problems. They're not big, complex applications, but they're problems that make lots of money for the corporations that are applying ChatGPT and neural network. Are there low-hanging fruit for quantum? Is that in quantum computing, or is it in quantum sensing? Any thoughts? Ilyas, do you have any views on that?
I don't know about low-hanging fruit, and it's certainly not a huge market, but I'm in Eleni's camp. I think that, and again, just being specific, so from next month, March, a leading French company called Thales, every one of its HSMs will be equipped with something called quantum origin that generates non-deterministic seeds for existing classical keys, which is massive. I don't need to tell people how important that is, and that's using an existing quantum computer, and it moves some of the load away from these questions about device independence. I think that I know that if Aronson was here, he'd be talking about the application that is around the corner for his random circuit sampling, if it could be certified. And I think they're working on something that will be announced quite soon, where an industrial organization is using it. And again, that's using a quantum computer for cryptography. So I think that is probably the low-hanging fruit in the short term. The more ambitious commentary by Xander from Microsoft about this tipping point when you get a certain number of logical qubits aligned with a high-performance compute, and they're talking about both biology and chemistry. I think it used to be speculative, but I don't think it probably is that. So I'm in the camp of Steve when somebody says, "Is that all?" I'm like, "What else is there?" So I don't have anything really more to add to that.
Okay. I want to see if there were any other questions that people have in the audience. Yes.
Hi. I just wondered, with funding, both government and private, what would you say in terms of convincing both parties to have sustained long-term funding that goes beyond any current trends or current government? Because obviously that is really what quantum is going to need to achieve these goals. So how are you going to convince them to keep funding, not just in not in the near term, but in the long term?
So sustained funding.
Yeah, I think maybe two things. I think it's kind of unrealistic or unreasonable to ask government to pay for quantum computing. Like, we have to build hospitals and do these other things that are super important, right? So I think it absolutely needs to be a partnership between private sector and government, and that's now possible. So a few years ago, I think it would be pretty challenging to raise that large amounts of money privately, but I think today this does look much more feasible. And then I think the second thing is, you see all these government strategy documents, and to be honest, they all look the same. Like, every country has the same strategy, so that's not a strategy. I think we need to be smarter about where we're spending the money, and I think we have to start realizing where our relative strengths are and then investing in those. Because if you spread the funding super thin, nobody's going to achieve anything. And guess what? Like, China doesn't have a spread thin strategy. Like, it has a singular goal to build a large-scale system. So I think we have to be smart at how we spend money.
It's interesting that the previous administration, previous government, in November 23, came up with 5 missions as part of the strategy. Quite specific. In fact, quite ambitious. You know, by 2035, UK-based quantum computers capable of 1 trillion quantum operations, 1 billion by 2030. By 2035, UK deployed first quantum network at scale, and several more, including, by 2030, every NHS trust benefiting from quantum sensing for brain scans and cancer detection. That's quite specific, which is quite helpful, quite ambitious. Any thoughts on how we're going to achieve these?
I was definitely an advocate for having missions even before joining UK Quantum, because I think it was quite clear we'd run out of road of just doing more collaborative R&D programs, allowing people to do things. To consolidate what we had, and I'll come back to this in a minute, we needed to set ourselves clear ambitions and goals to do that. To do that and to take businesses on the journey does require, to answer a part of the earlier question, a longer-term commitment, not sole funding, but it does need a commitment over years. Otherwise, from a company's point of view, it's just opportunistic money. You can't plan for anything like that if you don't know what's going to happen 6 months from now. But having the long-term ambitions, I think, was a good focus to help us understand what it is and to prioritise where that money goes. We still haven't got the plans just yet, but I do believe that's important. But the other thing I would say is, in putting together the plans to achieve them, we mustn't forget they also have to help support the development and growth of our industry as it is. What we don't want to do is suddenly go, oh, look, there's a shiny objective there, let's start trying to make that happen. So these things have a purpose, and that's both to bring things together, but also support the growth of our industry.
So I'm going to ask a question maybe related to that. It's about skills and training. Yeah, have we got the right kinds of skills to support innovation? Are we doing enough to broaden the skills base? And we heard of the numbers of PhD students, which is great, but not down at the master's or the bachelor's level or the technician level. What more would need to be done to enable the right kind of skills base to support wider growth in innovation and exploitation, scaling up? Ilyas, have you got any thoughts on that? And then I'll come to Eleni to respond as well.
Well, it will obviously take a village. Yeah, I think that look, in the United Kingdom, we're never going to compete with others in terms of money. We just don't have the money to compete with. I mean, somebody from Denmark was here today, and, you know, they're being bankrolled by Novo, and the French have got this determined France first. You know, they force their organizations to invest in French winners, and therefore have a very different model. And we talked about the vast amount of money just in Bavaria, never mind Germany. So this idea of being a little bit more skillful and determined in this next phase, meaning the next 10 years, I think the point that was made by others, then begs the question, how? You know, how can we be a little bit more smart? And I think it really does boil down to continuing and possibly extending our lead where we produce leaders, either in terms of small companies or in terms of individuals who can then create the demand for jobs here in the United Kingdom, and therefore well-paid jobs are the prompt for universities and the tertiary education system to give deeper roots. I'm not saying anything that probably every single person in this room would not have said. I think the tipping point for me, though, is going to be this here in the United Kingdom. I'll just speak about the United Kingdom. The tipping point for me is going to be, and we're not there yet, is where there are tangible success stories. And I'll just give two examples of what I mean by that. If we have a cadre of people who've been in startups, who've been successful and, I don't know, sold their options and bought off of Lancashire or something, you know, whether that's good or bad, I don't know. But, you know, you need to be able to point to these successes, and there's no way around that. We can't get away from the fact that that is something that motivates society as a level. And the other success, I think, is the one that everybody's mentioned here, which is at some point we do need to be able to look at a success, and it might be a standard, or it might be in quantum technologies, that allows that commercialization, because we in the United Kingdom aren't pushing our organizations. So in Saudi Arabia, Aramco's been told to do it. Total's been told to do it in France. In the United States, where we have a big operation, we have lots of corporates who now will invest money. That's not yet happening here. So that would be my rather simplistic but very straightforward opinion on that, what's needed.
So related to that, and I'll come to Jonathan, then I'll come to Eleni as well. Apprenticeships, undergraduate programs. Why aren't industry now clamoring for, we want to understand more about quantum, we want more people to develop at least some initial skills to allow them to be the right kinds of...
Industry at large, as in the end users.
Yeah, I mean...
Because they don't know what they want yet, or what they're doing with it. So it's very hard to push for skills and knowledge base in a workforce for a future you haven't quite worked out. Industry is notoriously bad at predicting what skills it needs. I mean, we are still running with, you know, AI was pretty much a surprise, big data was a surprise, cybersecurity, all of these things are still on the table, and industry gave about a year or 2 years notice for that, despite the fact that maybe even their internal R&D had been saying you'll need it. So end users at large, I think you'd forgive them, they don't quite know. I mean, I think we can look and go, we need to raise the level of awareness just across the board. Undergraduate programs, and we need to check that the curriculum before that is actually preparing students. It may not necessarily be teaching quantum mechanics, but ideally demystifying it or making it less of a surprise when we do. That would be a good thing. So I think we have to be realistic about industry at large. I mean, the quantum industry, I think that more of everything seems to be the...
Steve made a good point in your presentation earlier on today. You said there was about 500 people who are truly expert in quantum error correction. There's an opportunity to train 500 more and double the number, and in a sense, with a UK presence. So it's possible for either academia or industry or others to propose and promote and encourage the growth in particular areas that might be relevant to an economy, whether it's the UK or different parts of Europe. That's what you were advocating, wasn't it?
Yeah. I mean, I think this is such an amazing opportunity, right? I mean, quantum mechanics is exciting, physics is exciting, computing is exciting. You put the two together, you've got big companies, you've got CEOs of big companies talking about it. This is great publicity for quantum computing. I don't think we've ever had as many people talking about the field as we do today. And so people are excited about that, and they do want to know how can they get involved. We train people extensively at River Lane, not because we're like doing it for the better of society, but because we need those skills ourselves. And we're in a fortunate position that we've raised enough money that we know, we're going to need people in 2-3 years' time. We're going to recruit them today and train them up on error correction. Yeah. So some of our best leaders in River Lane came from other fields that had adjacent skills, and whether that's in software development or in particular areas of maths, there's a ton of interesting skills that are related to quantum error correction.
Okay, I'm going to take a last question at the back. Tim.
On the skills and training thing, it's quite a UK-centric question, but I'm going to ask it anyway. I think the UK government does appreciate the importance of skills and training, and we are getting a significant amount of funding put into that. But that's not the same as filling all the skills and training places with people. Now, most UK universities at the minute are running at a deficit because they've been encouraged over decades to sell UK education worldwide and encourage foreign students. And everyone's foreign student intake has gone off a cliff because loads of them are not now getting visas or getting ATAS to come into the UK. So we have all the skills and training places. I just am not convinced we have a strategy where we're going to fill all of those with people who can take them up and then stay in the UK and work. So I still think there's a problem. It's not just money that skills and training needs, it's actually the people intake.
Yeah, I agree. I think you're right, that people in their early careers come to a place and they end up creating roots there. They meet someone in a pub, one thing leads to another, and they get married, right? And they start a family. And then guess what? They stay there. It's hard to convince somebody in the middle of their career to move across the world. So I think it's a really valuable asset, if you like, for any country. And it's, mad not to invest more in that.
I would love us to continue on with this discussion, but we've reached the end of our time. So what I'd like to do is, first of all, thank the panelists for coming. If people can give a round of applause to the panelists. So what I'm going to close this session, and I'm going to be welcoming Lewis Barton from the Institute of Physics to talk about the next thing, but let's let the panelists lead the stage. Thank you very much. So I think this was mentioned earlier on. Lewis Barton's from the Institute of Physics, and he's going to be talking about the rest of the program for this year from a UK perspective. So I'll leave it up to you.
Thanks very much, Roberto. Great pleasure to be here. It was an excellent panel and been a fantastic event, I have to say. Thanks very much to Martin, to Sheila, and all the organisers for such a fantastic launch event. Really, I think showing, as Ilyas in the last panel said, how rich and vital the UK scene is and how connected it is internationally. So, hi everybody, my name's Lewis. I'm Director of Science at the IOP, the Institute of Physics, and as you probably know, the IOP are the professional body and learned society for physics in the UK and Ireland. We've got around 21,000 members, about half and half academia and business. We publish probably the best physics magazine in the world, Physics World, via IOP Publishing, and IOP Publishing are also here today. We've got 3 quantum special interest groups where members sort of network and strategize, and Anke Lohman, the chair of the Quantum Business Innovation and Growth Group, is here. We have an accelerator that's hosted many great quantum businesses, proud to have Orca Computing, for instance, as one of our alumni, and you heard from Richard earlier. So look, this isn't a sales pitch, but if you're into quantum and you haven't looked us up, do look us up. We're here to help. And for those who don't know me, my background is the civil service. So I put in place some of the early policy framework, not at the very beginning, but sort of bridging from phase 1 to 2 of the quantum policy approach, and then helped to play in the physics community's views into the most recent strategy, which I have to say is a fantastic strategy. And it's been a real pleasure to work with people like Sir Peter, with Roger, with Sheila, with DSIT, with DBT over many years, seeing this industry blossom and develop. So after a really rich set of talks on deep science and some perhaps hard truths on business innovation, I'm going to pull us back to where we started, the International Year of Quantum. So it's finally here, eh? I know we've all been counting the days. I certainly have been. It's like Christmas, you know, but it's finally arrived. I can't believe it. We're in the Year of Quantum. So let me set a bit of the scene and hopefully get you a bit excited about the year ahead in the UK and Ireland. So you heard a bit from Tom and from Peter at the start of the day about what the year is and why it's important. But I thought it was worth just saying this is probably the best supported international year ever, with more than 50 nations backing it. Really broad support with Mexico tabling it and then Ghana taking it to the UN General Assembly. It was approved a little bit late, so it took a little bit of a while for DSIT to ask us to coordinate, but we've been catching up very quickly. It's been great fun hitting the ground running. I think we've got ourselves into a really good place with a UK and Irish year that compares well internationally, and I expect will actually grow and develop even further as the year progresses. So one of the first things we did was agree the vision statement at the bottom of the screen there. And really that's saying we should be shooting at 3 targets. So celebrating with the community, as we're doing today, raising awareness with the public, and seeking to maintain and build the political momentum that we have. And it was great having Dave Smith, the National Technology Advisor at the international launch, saying that we have a strategy and we just need to deliver on it. So it should be a great opportunity during the course of the year to for more of those kinds of messages in the context of what's going to be a really important set of spending review decisions. So what are we doing? So this is not about the IOP doing everything. It's about us trying to make sure the basics are in place around the 4 audience groups, and then trying to help make them the whole more than the sum of its parts. So providing a bit of shaping narrative, showcasing, amplifying, and specifically that means representing on Peter's International Steering Committee, showcasing events on our website and on the international website, engaging UK and Irish stakeholders through various groupings, sharing and fostering ideas, and some cross-cutting support on comms and marketing. So that means things like facilitating a core narrative, so we can all be sort of singing from the same hymn sheets, seeding a bit of a media plan to try and cut through to the mainstream media, and also having a bit of fun, so looking at impactful stunts to cut through and raise awareness. And that means things like, you know, could we put Larry the number 10 cat in a box? You know, that's just edging out, I think, the idea of Brian Cox in a box. And we've been talking to Simon, for instance, at the Fraunhofer about the idea of relaunching the International Year Special Edition Glentanglement Whiskey. And talking to Cheryl about the ideas of projecting timelines of quantum on the GCHQ building, if that doesn't blow your cover. So look, we're in the market for creative ideas to try and cut through a little bit. So if you do have those kinds of ideas, please do get in touch. So what is actually planned? Let me give you a quick essentially a quick tour of the website, a few highlights of what's happening. And first, we'll start with the 3 core sort of audience groups facing activity. So policy-wise, Tom mentioned we expect this to be in early summer, but we're just finalising dates, and there'll be 2 main things. A week-long exhibition in Parliament. This could be pretty mega, and we'll be running a process soon to work out what kit we can feature and who we could bring to sort of tell that story to parliamentarians. And really, this is about reaching into those parliamentarians who don't know what they don't know. The types of people that Tom was talking about in terms of being a bit scared of the word quantum. So rather than being frightened of the word, we'd like them to be excited by the potential that it represents. And it's about talking about the solutions, not needing to know the detail of how the science works, but what can it do? So we'll work closely on this with DSIT and the cross-government user group, who have loads of great examples, and I'm sure it'll be a great opportunity for many of the organisations in the room today. We'll be complementing that with a session at the Science APPG, probably before the exhibition, to build a bit of momentum and engage the parliamentarians who know a little bit more about quantum. So that's a bit on policy. For the public and for schools, well, as Peter said earlier, one of the big opportunities of the year is to get a new wave of people interested in quantum. And we know there's a big shortage of skills, as we heard from the panel earlier. So, you know, where is the next generation? Where are those reskillers going to come from? So there's a couple of highlights of public and young people-focused activities here. So first of all, Mimi's Adventure. And this is about young people, obviously. So IOP has supported a series of books with Mimi as the main character. The first one was Mimi's Rainbow Adventure, about light, obviously. The second last year was on Mimi's Space Adventure. And this year, Mimi will be going into the world of the very small, Mimi's Tiny Adventure. And it's not just a book, it's also going to have a summer exhibition hosted in 37 Caledonian Road, our head office, so families and schools can come in and get engaged in an inclusive way about the quantum world. So other end of the telescope, public discourse, so bringing Jim Al-Khalili's amazing ability to explain and inspire beyond the science to the applications of quantum tech in the historic venue of the Royal Institution. I think he's going to be joining us here tomorrow also, which is wonderful, a fantastic ambassador. And we're going to be preceding that discourse with a day of careers inspiration for older school children and complement that with short videos for social media involving some of the TikTok influencers that we've been working with through our Limitless campaign. And they've allowed us in the past to reach many millions of people, so we're hopeful this can really help us to cut through. So a few different segments of the public there. That leaves us with community celebrations. So there's lots going on across the year, but I just want to draw your attention to the first week of November. That's going to be a big highlight. So please mark your calendars. So we're essentially topping and tailing the National Quantum Technology Showcase event with, well, as we've just talked about, the public-facing activity towards the end of the year, end of the week, and more community-focused activity towards the beginning of the week. So essentially it's a two-day event focused on one day the history of quantum, one day on the future, where could we go over the next 10 years, and the agendas are being curated by the IOP History of Physics group and Quantum Business Innovation and Growth groups, respectively. So we're expecting this week in the round to be a draw for international delegations, with the combinations of celebrations, showcasing, and we're discussing with DCIT, with Innovate UK, the Royal Society, UK Quantum, etc., to try to make this week a real centrepiece that talks to how the UK is connected internationally. Worth just mentioning IOP Publishing, also doing a huge amount. So you might have spotted their dedicated quantum-focused careers guide that's already out there. Some of the specials in Physics World have already been launched. So there was a front page on Helgoland. There's been some really successful content, for instance, on why Bohr got things wrong, also a spot on the International Launch Event. And there's going to be lots of exciting future-gazing content in journals like QST, the Quantum Science Technology Journal, and that will also feed into some of the stuff we'll be highlighting through events, as well as a whole series of podcasts, web stories, etc. It's a really, really rich offering, and they've got a dedicated page hosting it all, so do check it out. So I've talked a bit about detail. Let me just zoom back and very briefly give you a sense of how this sort of fits into a wider calendar of events. So it's worth saying there's now more than 30 events in the UK and Irish calendar, which is an event every 2 weeks or so. And there's many more internationally, so I'm hoping the quantum community is not going to spend all its time during this year at events, but will actually be able to get something done. And it also means there's too much here to sort of talk about it all, but please check out the website after. So yeah, just give you a bit of a flavour of it. There's a real mix of stuff here, everything from academic conferences to business or finance-focused events. Some of it is specially created for the year, some of it is regular activity that will have a bit of an extra boost from the year. I'll just pull out a few sort of national highlights, as Peter highlighted. This is very much a whole nation celebration. So the World Quantum Day, 14th of April, that's going to be the big centrepiece for the Irish activity, and they're putting in place some really exciting plans, which we'll be able to say more about soon. I'll just skip through because there's a few of these slides. So much of the activity on this slide is in and around the Quantum Fringe in Scotland, where we expect to have a national hackathon, and we're hoping that will also be the node of a broader global hackathon event, which will be really, really good fun. And then moving on, I've talked a bit about the close of the year with the Quantum Week in November, but another highlight just put out on this side. So we're really pleased that the City Quantum Summit is going to be running again this year. It's such an important event, I think, for the business and finance communities to come together. So, there's a real breadth of stuff, and we're still finding events that we haven't featured that we should be featuring. So please do let us know if you know of things that feel like they should be here and aren't. Last but not least, a quick plug. So we're really keen that there are strong quantum nominations for our awards program this year. The Business Awards is still open, it closes on the 28th of March. We've had some great companies winning those awards in the past, so please do make a nomination if you think there are some companies that should be being celebrated. And yeah, call to action, so please check out the website, the IOP and IOPP websites, as well as the international one. Please let us know if you're planning anything that's not featured. Let us know also if you have creative comms ideas, or if you have announcements that would benefit from more exposure. And even if you're just curious about sort of what's going on, do get in touch. If you'd like a bit more profile for your brand or your organisation, keen this is a year that's genuinely for the whole community, and we have lots of sort of partnerships and sponsorship opportunities. So do please get engaged. So yeah, I hope that's given you a bit of a flavour of what's to come. I hope you're looking forward to talking more about quantum during the course of the year, and using the year to celebrate, to engage, and to maintain momentum. So I'll hand back to Roberto now for some closing remarks.
Great, if we can, So thanks very much, Lewis. So all I've got to do now is to thank some of the organisers. In fact, I should get them to stand up. They're in the room. Come on, Kaylee and Martin and James and Lee. Maybe James is coming tomorrow. Oh, no, there he is. There is another person, Ellen Kashefi, who wasn't able to come due to other issues. And any others? Giora, where is she? Yeah, at the back. Great. Okay, well, let's give them a round of applause for organising this conference. So I'd also like to thank the Royal Society Audiovisual and Catering and industry teams for keeping us fed and all the things we need to do today. Last of all, I want to thank all of you who've come today, taking your time out to attend this conference. And note that the second day of the conference will be held here, same place, 9:30 tomorrow. So with that, I'll close the conference. There is an event for the speakers and some other invitees who've got either yellow little dots or blue dots, which would be taking place where we had the coffee outside. But other than that, thank you all for coming today.